universe is a colossal place, teeming with endless wonders and mysteries. From tiny particles to vast galaxies, it goes beyond what our minds can fully grasp. There are billions of galaxies out there, each packed with millions or even billions of stars. These stars and their planets form solar systems that float through the universe. Come along as we take a journey through space, diving into the astonishing wonders of the cosmos, from the well-known to the untold. The Sun, a medium-sized yellow dwarf star, is the heart of our solar system, and it's crucial for life on Earth. This star, sitting roughly 93 million miles away, creates energy through nuclear fusion, where hydrogen atoms merge, forming helium and letting off a massive amount of light and heat energy. For nearly all life on Earth, this sunlight is the main energy source. Plants soak up this light for photosynthesis, turning light energy into chemical energy and making oxygen, a critical element for most life forms to survive. Without a constant stream of solar energy, Earth's temperatures would drop, oceans would freeze over, and life as we know it would disappear. The Sun's gravitational pull is also vital in keeping our solar system stable. Its huge gravitational force holds Earth and the other planets in their paths, keeping them from drifting into the cold plains of space. Earth's journey around the Sun, taking a year to complete, creates the seasonal cycles. These changes in seasons have a big impact on ecological systems and farming methods, supporting a variety of life forms to thrive. Furthermore, the Sun sends out solar wind, a flow of charged particles that clash with Earth's magnetic field, sometimes creating amazing light shows like the auroras. So, the Sun isn't just a glowing gas ball, but a life-giving engine, deeply connected to Earth's ecological balance and life cycles. Our solar system's journey started more than 4.5 billion years ago, within a giant molecular cloud of gas and dust. This cloud, mostly made of hydrogen and helium with tiny amounts of heavier elements, was part of a nebula, a star nursery where stars and solar systems come to life. It all kicked off when a part of this molecular cloud got upset, maybe from a supernova blast nearby, causing the cloud to collapse under its gravity. As it collapsed, it spun, forming a protostar at the center, which would light up to become our Sun. The leftover stuff around it flattened into a protoplanetary disk due to keeping the spin going. Inside this disk, particles began bumping and sticking together, gradually forming bigger clumps through accretion, which is like cosmic building block stacking. These clumps, known as planetesimals, became planets' building blocks. Over time, planetesimals merged into protoplanets, growing by pulling in more material with gravity. In the hot inner zones near the protostar, only metallic and rocky stuff could form, leading to planets like Earth and Mars. Further out, where it was cooler, gas giants like Jupiter and Saturn, mainly made of hydrogen and helium, came to be. Beyond these giants, icy bodies and comets formed. What started as a cloud of gas and dust became our detailed solar system, showing off the universe's dynamic and changing nature. Within our solar system, every planet stands out with unique traits, adding to the rich mosaic of our celestial neighborhood. Starting with Mercury, the planet closest to the Sun, it's a small rocky world with insane temperature swings, reaching almost 800 degrees Fahrenheit during the day and dropping to about minus 330 degrees Fahrenheit at night. Without an atmosphere to balance these temperatures and being heavily cratered like our Moon, Mercury indicates a geologically inactive surface. Venus, known as Earth's twin because of its similar size and form, has dramatically different environmental conditions. Veiled by thick clouds of sulfuric acid, Venus endures scorching surface temperatures around 900 degrees Fahrenheit, making it the hottest planet in our solar neighborhood. It's caught up in a runaway greenhouse effect, with its thick carbon dioxide atmosphere trapping heat intensely. And instead of turning like most planets, Venus spins backward, causing the sun to rise in the west and set in the east. Earth is the only planet blessed with liquid water and abundant life, keeping a steady climate thanks to a mixture of oceans, an atmosphere packed with nitrogen and oxygen, and a protective magnetic field. Mars, with its rusty iron oxide surface, boasts Olympus Mons, the tallest volcano in the solar system, and Valles Marineris, a canyon system that dwarfs the Grand Canyon. Although dry now, Mars has polar ice caps and hints that water once graced its surface. Jupiter, the mighty gas giant, mainly made of hydrogen and helium, is famous for its great red spot, a giant storm larger than our planet and still raging after centuries. As another gas giant, Saturn is famous for its amazing rings made of ice and rock particles that circle the planet. Uranus is quirky with its extreme tilt, rotating on its side, which makes its seasonal changes rather unique. Its blue-green hue comes from atmospheric methane, and it has a faint ring system. Neptune, the farthest planet, is whipped by supersonic winds over 200 miles per hour, with a striking deep blue color also because of methane. This distant planet features dark storm spots akin to Jupiter's. Pluto, demoted to a dwarf planet, still fascinates with its icy face, heart-shaped glacier, and 5 known moons, including the large Charon. Each planet's unique traits add rich detail to the solar system's tale, capturing the sheer scope of conditions and compositions within this cosmic neighborhood. The rocky inner planets, Mercury, Venus, Earth, and Mars, differ greatly from the outer gas giants Jupiter, Saturn, Uranus, and Neptune in makeup, structure, and atmosphere. The so-called terrestrial planets are mainly silicate rock and metal, sporting solid surfaces complete with mountains, valleys, and craters. And Earth and Mars even have signs of volcanism and tectonic activity. Their atmospheres, if they have them, are thin relative to the planet's size. Earth's atmosphere sustains life, but Venus's thick toxic one, packed with carbon dioxide, leads to an intense greenhouse effect. On the flip side, gas giants are mostly hydrogen and helium without solid surfaces. Jupiter and Saturn, the biggest ones, have thick gaseous layers, likely atop rocky metallic cores. They sport swirling clouds, storms, and massive magnetic fields, with Jupiter housing the famed Great Red Spot, a massive, long-lasting storm. These giants also host a large number of moons, with Jupiter having at least 79 and Saturn over 60. Their ring systems are elaborate, especially Saturn's bright and well-known rings. Uranus and Neptune, labeled ice giants thanks to their significant frozen water, ammonia, and methane, slightly differ from the larger gas giants. Uranus spins on its side, probably from early massive impact, showing faint rings and a chilly blue-green look from methane. Neptune, being the most distant, is known for its vibrant blue and wild weather, home to storm systems like the Great Dark Spot. Inner rocky planets are small, dense with a solid crust, whereas the massive outer gas giants are less dense, made mostly of gas and ice with no solid surface. These differences highlight the range of planetary formations and conditions possible within a single solar system. The moons scattered throughout our solar system provide a fascinating look at a wide range of astronomical bodies, each with features making them special. Europa, one of Jupiter's Galilean moons, is of particular interest due to its potential for harboring life. Underneath its icy covering, there's a hidden ocean on Europa, kept warm and fluid by the powerful gravitational pull of Jupiter. This enormous ocean might hold more water than all of Earth's seas put together, sparking fascinating questions about the possibility of life. Meanwhile, Jupiter's moon Io is famous for its wild volcanic show, being the most volcanic spot in our solar system, with explosions that send out clouds of sulfur and sulfur dioxide far into the cosmos. Io's surface continuously shifts with sulfuric lava flows and vast calderas, all shaped by the gravitational forces at play involving Jupiter and its neighboring moons, Europa and Ganymede. Speaking of Ganymede, it's the biggest moon around, even outsizing Mercury. It stands out because it has its own magnetic field, a rare find for a moon, hinting at a possibly liquid iron or iron sulfide core. This magnetic magic helps create Ganymede's auroras, similar to Earth's, but with the added twist of Jupiter's magnetic influence. Saturn's moon Titan also demands attention, with an atmosphere packed with nitrogen reminiscent of early Earth. Titan's hidden world under a thick orange haze reveals lakes and rivers of liquid methane and ethane, along with a guessed-at subsurface ocean of water mixed with ammonia deep below, opening multiple doors for possible biological life. The moon's air mix and how it behaves on the surface make it a top spot for future missions aimed at uncovering early life conditions and finding signs of life. Then there's Saturn's moon Enceladus, which fascinates scientists with stunning geysers that stream water vapor, ice, and organic materials from its south pole. These suggest another underground ocean is lying beneath, turning Enceladus into a hot topic in the hunt for alien microbes. The material shot out by these geysers adds to Saturn's E-ring, offering a one-of-a-kind chance to indirectly explore environments that might support life via spacecraft. Let's not forget about Neptune's moon Triton, which is peculiar due to its backward orbit, hinting at its capture by Neptune's gravity instead of forming right there. Triton shoots out nitrogen gas, hinting at activity beneath its frozen reflective surface made of water and nitrogen ice, with a bizarre cantaloupe landscape that still leaves scientists baffled. This mix of odd orbit and surface activity makes Triton a riveting subject for understanding captured celestial bodies' dynamics. These moons display an incredible variety of geological, atmospheric, and possibly even biological features, each adding its unique piece to the puzzle of planetary science and the hope of finding life beyond Earth. Meanwhile, the asteroid belt hanging out between Mars and Jupiter's orbits plays a fascinating role in our solar system's story. Made up of numerous rocky remnants of failed planet formation dreams, the belt is home to fragments ranging from tiny specks to massive chunks hundreds of miles across. All its objects together weigh less than our moon, acting like a cosmic border between the solid inner planets and the gaseous outer titans, formed from the solar system's early dust cloud. A big influence of the asteroid belt is felt on Earth's journey through time. Sometimes the gravitational push and pull, especially from Jupiter, flings asteroids from their safe zones, turning them into potential Earthbound sections of rock. These space rocks occasionally hold stories of Earth's past catastrophes, like the infamous asteroid that helped drive the dinosaurs to extinction 66 million years ago, and they offer crucial clues when captured and studied, since they carry the ancient solar system's untouched materials. Moreover, the asteroid belt serves as a vibrant space lab for grasping how planets form and take shape. The belt's larger members, like Ceres and Vesta, have become subjects of deep exploration, shedding light on these processes as we continue to learn about our celestial neighborhood. Ceres, known as a dwarf planet, has intriguing signs of water ice and possible cryovolcanism, suggesting it's got some complex geology going on. Vesta, however, has a layered structure much like Earth's planets, complete with a core, mantle, and crust, which implies it melted internally at some stage. Plus, the asteroid belt might be a treasure trove for future space explorers. There's iron, nickel, and even water in ice form out there in those asteroids. Some scientists and entrepreneurs are getting pretty excited about asteroid mining, which could supply key materials for long-term space travel and living, cutting down on how much we need to haul from Earth. Comets, often called dirty snowballs, are pretty important in the solar system with their mix of ice, dust, and organic stuff. They're mostly from faraway icy spots, like the Kuiper Belt and Oort cloud. As they head toward the sun, they put on quite a show, changing dramatically and offering clues about the early solar system. When a comet gets near the sun, its ices start turning into gas, creating a glowing coma around it and often amazing tails that stretch millions of miles. These comets are basically ancient relics, sticking around for over 4.5 billion years and acting like time capsules full of early solar system secrets. By studying them, scientists gather clues about the solar nebula that birthed the planets. Missions like the European Space Agency's Rosetta, which landed on Comet 67P Churyumov-Gerasimenko, have unearthed complex organic molecules, shedding light on life's building blocks. Comets also played a big part in Earth's story. It's thought they delivered water and organic molecules to early Earth, which might have been crucial for life to kick off. Similar isotopes suggest these cometary collisions were key in seeding our planet with life's ingredients. Comets also shape planetary atmospheres and geological history, sometimes with dramatic effects. They've been linked to major atmospheric shifts and maybe even mass extinctions. Their role in spreading organic materials and water across the solar system and their interactions with planets highlight their influence in shaping its evolution. Comets aren't just wandering ice balls. They're vital to understanding the solar system's history, present dynamics, and future. They reveal primitive materials that formed planets and possibly played a key role in delivering life's essentials to Earth, while still affecting our neighborhood's dynamics and chemistry. The Kuiper Belt and the Oort cloud are crucial in framing our view of the solar system's limits, acting as reservoirs for countless icy bodies and hinting at how the solar system formed and evolved. The Kuiper Belt is a disk-like area beyond Neptune, stretching from about 30 to 50 astronomical units from the Sun. It holds thousands of small icy bodies, including dwarf planets like Pluto, Haumea, and Makemake. Discoveries here, especially since the late 20th century, have reshaped our view of the solar system's outer reaches, proving it's much more vast and intricate than once assumed. The Kuiper Belt is key for understanding where the gravity of major planets gives way to the more scattered outer regions. The diverse compositions and orbits of Kuiper Belt objects suggest they've largely stayed the same since the solar system's early times, preserving untouched materials from the solar nebula. These objects give us crucial clues about how planets came together and moved around. Plus, features like the scattered disk, filled with objects on wild orbits way beyond the Kuiper Belt, suggest Neptune and other far-off planets had a hand in shaping how our solar system looks today. Imagine a massive area known as the Oort cloud, stretching somewhere between 2,000 and 100,000 RU from the Sun. Many think it's where long-period comets, a big deal due to their extensive orbits lasting thousands to millions of years, come from. Even without direct sightings because of the distance, the Oort cloud is key for updating theories on these comets' origins. Various models propose the Oort cloud came from leftover gas and dust surrounding the young sun, scattered outward by the pull from giant planets and passing stars. Combined, the Oort cloud and Kuiper Belt help us figure out where the solar system technically ends and interstellar space kicks off. They show that the sun's gravity reaches well beyond the known planets. Checking out these far-off regions sheds light on how our solar system formed, how planets migrated, and how it interacts with nearby stars and the galaxy around it. Thus, Pluto, which was once the 9th planet before being rebranded as a dwarf planet in 2006, keeps scientists and curious minds captivated because of its complex traits and insights into the outer reaches of space we live in. A major draw of Pluto is its lively surface landscape. Contrary to most bodies in the Kuiper Belt, Pluto isn't some cold, inactive world. Thanks to NASA's New Horizons mission in 2015, we got a peek at Pluto's surface full of surprises, like large plains of nitrogen ice, tall mountains made of water ice, and signs of ongoing geological changes. Take Sputnik Planitia, for instance, a heart-shaped icy plain thought to be a massive moving glacier in a giant basin from a previous collision. Pluto's atmosphere is another striking feature. Made up mainly of nitrogen, along with some methane and carbon monoxide, this thin layer changes with the seasons, expanding as Pluto gets closer to the Sun, sublimating ice to refill it, then freezing when further away. These changes highlight complicated interactions between Pluto's surface and atmosphere, even way out there. Pluto's group of moons adds to the mystery. Charon, the biggest, is so massive that the center of gravity is outside Pluto itself, making them a duo. Charon itself has interesting features like huge canyons and a dark spot called Mordor Macula at the pole. The behavior between Pluto and Charon provokes questions about their tidal effects and shared history. The smaller moons, Styx, Nix, Kerberos, and Hydra, spin chaotically, probably due to the gravity play between them and Pluto-Charon. From an astrobiological angle, Pluto teases with the potential for molecular processes that could reveal more about foundational organic chemistry. While it's too cold to expect life as we know it, organic molecules on the surface, formed by sunlight and cosmic rays affecting nitrogen and methane, are pivotal for learning about early chemistry in space. Pluto, thanks to its engaging atmosphere, dynamic surface, intricate geological past, and intriguing moons, remains a subject of intrigue, underscoring the unexpected intricacy small icy worlds can hold. Studying Mercury helps us get a better grasp of how different processes work together on planets, especially those way out in the solar system, where ice, geology, and atmospheric changes play out in environments completely different from what we see. Closer to the Sun. Take Mercury, the closest planet to the Sun, full of fascinating details that catch the interest of astronomers and fans alike. One of the most amazing things about Mercury is how wildly temperatures swing. It doesn't have much of an atmosphere to keep the heat, so temperature on the surface can really flip. During the day, it can get scorching hot, nearly 800 degrees Fahrenheit, and then drop to freezing levels at night, hitting around minus 330 degrees Fahrenheit. This big change shows how much of the Sun's intense heat the planet gets during the day and how quickly it loses it at night. Mercury also has a rich geological story, evident from its surface, which is covered in craters kind of like the Moon. One big standout is the Caloris Basin, one of the largest impact craters in the solar system, stretching over 960 miles. It's a huge reminder of dramatic events in Mercury's past. Around this area, you'll find chaotic ground, likely formed from the impact shock waves. The surface has big, smooth plains that seem to be old volcanic land and massive cliffs known as scarps. Some stretch for hundreds of miles and tower over a mile high. It's thought these scarps are from the planet slowly cooling and shrinking over billions of years, making the crust fold over itself. Plus, Mercury has a large iron core, taking up about 85% of its radius, which is unusual for a rocky planet. Even though its magnetic field is only about 1% as strong as Earth's, the fact it has one means the core is at least partly molten. This gives experts clues about planetary magnetism and how planets evolve thermally over time. Despite being relatively close to Earth, Mercury can be a tricky planet to observe because it's so near the Sun. But missions like NASA's MESSENGER, which orbited the planet from 2011 to 2015, have given us loads of new information about this small, dynamic spot in space. MESSENGER data revealed unexpected finds, such as water ice in craters near Mercury's poles that never see the Sun. These icy patches, protected from sunlight, hint at ice being brought by comets or asteroids. Mercury's unique orbit also adds to its puzzling nature. It has an oval-shaped orbit and zooms around the Sun in just 88 Earth days. With its 3-to-2 spin-orbit resonance, it rotates 3 times for every 2 laps around the Sun, resulting in 1 solar day equal to 176 Earth days. Mercury's extremes in temperature, its features like vast, ancient volcanic plains and huge cliffs, a disproportionately large core, hidden water ice, and unusual orbital quirks make it a captivating focus for planetary science. Meanwhile, Venus, the hottest planet in the solar system, owes its extreme heat chiefly to a runaway greenhouse effect. This happens when there are enough greenhouse gases in the atmosphere to trap a lot of heat continually, pushing surface temperatures higher and higher. Venus's atmosphere is mostly carbon dioxide, about 96%, covered in thick clouds of sulfuric acid, playing a vital part. Here's how it works. Sunlight breaks through to reach Venus's surface. Once it's absorbed, it gets sent back out as heat. On Earth, some of this heat escapes, but Venus's dense carbon dioxide acts like a giant warm blanket, leaving heat stuck inside. The continuous trapping of heat ramps up the temperatures both in the atmosphere and on the surface, creating a never-ending loop. When things heat up, they hold on to more warmth, making it even hotter. That's why Venus is scorching at about 900 degrees Fahrenheit on average, surpassing Mercury, which is closer to the Sun but doesn't have a thick atmosphere to trap heat. Venus's atmospheric pressure is about 92 times what you'd find on Earth at sea level, adding to the intense heat by pressing down, trapping warmth, and intensifying the greenhouse effect. Sulfuric acid clouds also reflect sunlight, stopping the surface from losing heat, while scattering light to evenly spread the heat across the atmosphere. Venus is a fascinating case, highlighting the serious impact of greenhouse gases. Scientists think Venus once had a milder climate, possibly with liquid water. But as the sun's rays grew stronger, the water likely evaporated, releasing more water vapor, a strong greenhouse gas, causing even more warming. This chain reaction turned Venus into the hottest, most inhospitable place you see today. Its thick atmosphere full of carbon dioxide is the culprit behind this relentless greenhouse effect. Studying Venus helps us understand how greenhouse gases can drastically influence a planet's climate and maintain the delicate balance needed for life. Meanwhile, Mars, often called the Red Planet, is home to some captivating geological marvels that spark both curiosity and serious scientific exploration. One standout feature is Olympus Mons, the tallest volcano in the solar system. It soars to about 13.6 miles high, nearly 3 times taller than Mount Everest. This shield volcano is like those in Hawaii, just way bigger. Another amazing Martian feature is the Valles Marineris, a vast canyon system stretching over 2,500 miles long with depths of up to 4 miles. It dwarfs the Grand Canyon and was likely formed by tectonics and surface collapse from the crust being pulled apart. This canyon gives us deep insights into the forces shaping Mars, pointing to a complex history involving crust movements and likely volcanic activity. Mars also has signs of ancient water flows, seen in outflow channels and valleys that show water once carved paths across the planet. For example, the extensive channels of Ares Vallis and Ma'adim Valles seem shaped by sudden flooding, while valley networks like Nanedi Valles suggest sustained water flow ages ago, hinting at potential past life on Mars. Its plains, dunes, and icy polar caps, changing size with the seasons, tell of ancient oceans and a dynamic, sometimes violent history. The northern plains, like the Vastitas Borealis, might be old ocean beds, while the southern highlands are heavily cratered, revealing more of Mars' wild past. The polar regions catch the eye with layers of water and carbon dioxide ice, dry ice, that change with the seasons and offer insights into the planet's climate history. Plus, chaotic terrain full of randomly scattered large boulders adds a layer of mystery, perhaps from underground ice melting and collapsing. Mars isn't just fascinating to study for its geological quirks. Those features also hold vital clues about its climate, volcanic activity, processes on the surface, and whether it might have been habitable. Each new find, like gigantic volcanoes, old riverbeds, and puzzling chaotic terrains, helps us piece together Mars's story and its potential for life, expanding our exploration of the solar system. Over on Jupiter, the atmosphere is a wild mix of hydrogen, helium, ammonia, and other trace gases, where the famous Great Red Spot was born, a massive, long-lasting storm that's been going strong for at least 350 years, quite possibly longer. This storm is a clear proof of Jupiter's intense atmospheric dynamics. It's fueled and sustained by Jupiter's fast spin, completing a rotation in just about 10 hours, which results in powerful jet streams that zip east and west, forming cloudy bands that wrap around the planet. Known as zones and belts, these bands move in different directions and speeds, leading to violent clashes of gas. The Great Red Spot sits in one such clash zone between a westward belt and an eastward zone, which helps keep it twirling. This storm is an anticyclone spinning counterclockwise in the southern hemisphere, and it boasts a high-pressure center. Unlike earthly cyclones, which tend to lose steam, Jupiter's Great Red Spot is continually energized by the planet's internal heat, which exceeds what it gets from the sun. This heat powers the convection currents that drive the banded winds and storms and keeps the Great Red Spot alive. Its deep roots run possibly 200 miles below the clouds, adding to its longevity. The storm's signature red shade is still a bit of a head-scratcher, but is thought to be due to complex chemical reactions from exposure to solar ultraviolet light and the planet's specific atmospheric setting. There's a chance that compounds like ammonium hydrosulfide and possibly other chemicals like phosphorus or sulfur are behind the red tones. These can react in Jupiter's lively upper atmosphere, creating the vivid look. The storm's red tint can change over time, hinting at shifts in its chemical makeup or internal happenings. Beyond its color and age, the Great Red Spot is enormous. It once spanned over 25,000 miles, big enough to fit 3 Earths side by side. However, it's been shrinking in recent decades, now measuring about 10,000 miles across. Even with its reduced size, the Great Red Spot remains the solar system's largest known storm. Meanwhile, Saturn's rings steal the show in our solar system with their massive size, brightness, and complexity, distinguishing the planet from others. These rings are especially striking compared to those of other gas giants, Jupiter, Uranus, and Neptune, and can even be seen with small telescopes. Made mostly of countless ice and rock particles, ranging from fine grains to large boulders, the rings are impressive in size and structure. They stretch 175,000 miles from Saturn's equator, yet remain shockingly thin compared to their width, with thickness ranging from about 30 to several hundred feet. There are 7 main sections, labeled A through G, based on discovery, with the A, B, and C rings most prominent. These are separated by gaps, such as the Cassini division, a 2,920-mile wide gap between the A and B rings, where fewer particles exist due to gravitational pulls from Saturn's moons, especially Mimas. What's more, Saturn's rings are notable for their vivid brightness. They're made largely of water ice, which reflects sunlight well, giving them a luminous glow when observed from Earth. The ice particles in Saturn's rings reflect a lot of light, giving them a stunning, almost otherworldly glow that stands out against the darker, less noticeable rings of other gas giants. Beyond just being beautiful, Saturn's rings show a lot of movement and intricate designs. The planet's numerous moons, over 80 have been discovered, exert gravitational forces that cause the formation of smaller rings, waves, and gaps. Some of these smaller moons, called shepherd moons, help keep the rings sharp-edged. For instance, Prometheus and Pandora shepherd the F-ring, using their gravity to manage its particles and maintain its distinct, braided look. These gravitational forces lead to captivating events like spiral density waves and bending waves, which move through the ring particles and offer clues about the physical laws that control disk systems in the universe, from planetary rings to the young stars surrounding disks. Another unique feature of Saturn's rings is how they change with the seasons, influenced by Saturn's 27-degree axial tilt. As Saturn travels around the Sun, which takes nearly 30 years, the angle at which sunlight hits the rings changes. This cycle creates alternating periods of bright illumination and near invisibility. These shifts allow scientists to study the composition and structure of the ring particles from different viewpoints. The mysterious origins of Saturn's rings also add to their appeal. While scientists aren't exactly sure how the rings formed, popular theories include the breakup of a comet, the destruction of an icy moon, or leftover material from Saturn's formation. These ideas suggest the rings are relatively young, less than 100 million years old, and temporary in geological terms. With their enormous size, dazzling brightness, detailed patterns, and dynamic behavior, Saturn's rings are fascinating. Combined with the intriguing gravitational influences from Saturn's moons and the mystery of their origin, these rings are not only the most noticeable, but also the most scientifically engaging ring system in our solar system. Studying them continues to improve our knowledge of how planetary rings work, the history of Saturn, and the bigger picture of disk systems in space. Now, picture a planet spinning almost horizontally, like a top that's been knocked over. That's Uranus, the seventh planet from the Sun, with an axial tilt of 98 degrees. Unlike Earth's 23.5-degree tilt, Uranus's extreme angle gives it the wildest seasons in the solar system. Imagine this. For about 42 Earth years, one pole is stuck in a long, cold winter, while the other is in endless daylight. As Uranus completes its 84-year orbit, the roles flip, with each pole experiencing extreme shifts between freezing cold and blazing sunshine. The reason for Uranus's odd tilt is still debated, but a leading theory is that a massive object about the size of Earth crashed into it in the past. This collision likely caused Uranus to tip over, resulting in its strange position. Because of this tilt, Uranus experiences dramatic atmospheric changes and unusual weather patterns. Scientists think these intense seasons might stir up significant changes in the atmosphere, potentially creating supersonic winds and complex cloud patterns that can be seen from Earth-based telescopes. These features make Uranus a fascinating subject for both amateur astronomers and professional scientists, showcasing a cosmic dance of light and darkness that highlights the intricate and astonishing nature of celestial dynamics. Neptune, the eighth and most distant known planet in our solar system, exhibits some of the wildest and strongest weather patterns, including winds that tear across its surface at speeds of up to 1,300 miles per hour. These winds, which move faster than any hurricane or typhoon on Earth, are one of this distant blue giant's biggest mysteries. At mind-blowing speeds, Neptune's winds can tear clouds apart and mix gases in a dramatic display of atmospheric chaos. Even though the planet is incredibly far from the Sun, which makes its average temperature drop to a chilly -373 degrees Fahrenheit, its atmosphere still supports these ongoing storms. The reasons for Neptune's intense winds remain a mystery. One popular idea is that the planet's internal heat, unexpectedly high for its place in the solar system, could trigger this wild weather. Neptune is thought to emit more than twice the energy it receives from the Sun, hinting at an internal heat source, possibly from the slow gravitational compression of its fluid core. This internal heat might stir up convection currents, causing huge temperature differences that power violent storms and fierce winds. Another mystery is how these storms keep their strength without quickly dying down. The Great Dark Spot, a huge storm system similar to Jupiter's Great Red Spot, is an example of these powerful and somewhat long-lasting weather phenomena. These curiosities make Neptune an exciting topic to study, and scientists rely on telescopic data and Voyager 2's flyby for insights into the forces shaping one of the solar system's stormiest atmospheres. When scientists look beyond our solar system, they've come up with clever ways to study planets orbiting stars many light years away, known as exoplanets. One key technique is the transit method, which takes advantage of the small dimming of a star's light when a planet passes in front of it. If this tiny drop in brightness happens regularly, it indicates an exoplanet's presence. Observatories like NASA's Kepler Space Telescope have famously used this method, discovering thousands of exoplanets by observing many stars at once for these slight fluctuations. Another intriguing technique is the radial velocity method, also called the wobble method. When a star has an orbiting planet, the planet's gravitational pull makes the star move a bit in its own small orbit. This movement causes shifts in the star's light spectrum, seen as alternating blue and red shifts due to the Doppler effect. By carefully tracking these spectral changes, astronomers can figure out the planet's mass and its distance from its star. Alongside these techniques, direct imaging, although tough because stars' brightness tends to outshine their planets, has achieved great success with advanced tools like coronagraphy that block a star's light to spot the faint glow of orbiting exoplanets. These methods together create a richer view of the universe, helping scientists infer the size, composition, and even the atmosphere of these far-off planets. While each method has limitations, their combined data sets push the boundaries of our knowledge, bringing us closer to answering big questions about the possibility of life and the variety of planetary systems across the galaxy. When we take a closer look at the Sun, the heart of our solar system, we see it made of several distinct layers, each playing a special part in its structure and functioning. At its core, the Sun acts like a powerhouse, with temperatures soaring to about 15 million degrees Celsius. Here, nuclear fusion happens, where hydrogen atoms become helium, releasing a massive amount of energy in the form of light and heat. This energy takes thousands to millions of years to travel outward from the core, gradually moving through the radiative zone, where it's absorbed and re-emitted by atoms in a slow, zigzagging journey. Surrounding the radiative zone is the convective zone, where the temperature drops enough for energy to be transported by convection currents. Hot plasma rises to the surface, cools down, and sinks back down to be reheated, creating a boiling, chaotic environment, much like a pot of soup on the stove. Above this, we reach the Sun's visible surface, called the photosphere, featuring a cooler temperature of about 5,500 degrees Celsius. This is where sunlight starts its journey into space, and you can spot sunspots, those cooler, magnetically active areas. Just above that is the chromosphere, which appears as a reddish glow during solar eclipses. Even further out lies the corona, the Sun's outer layer. The corona is astonishingly hotter than the layers beneath, hitting temperatures in the millions of degrees Celsius, leaving scientists scratching their heads for years. It's in the corona where the solar wind begins, releasing streams of charged particles that affect space weather, impacting planets across the solar system, Earth included. Each layer of the sun, from its super-hot core to its distant corona, plays a role in the processes that keep the sun shining brightly and affect the entire solar system. The sun's monumental power comes from nuclear fusion, where hydrogen turns into helium, releasing immense energy that lights and warms our solar neighborhood. Deep in the sun's core, where temperatures soar to an incredible 15 million degrees Celsius and pressures hit staggering levels, hydrogen nuclei get close enough to overcome their natural repulsion and collide. As these protons smash together, they fuse into helium nuclei through a series of interactions called the proton-proton chain reaction. During these reactions, a tiny bit of the hydrogen mass turns into energy, following Einstein's famous equation E equals mc2. This formula explains that even a small amount of mass can become a big amount of energy. The energy created in the core starts its journey outwards, moving first through the radiative zone as photons bounce around for thousands to millions of years. When this energy reaches the convective zone, it moves via turbulent currents of rising and sinking hot plasma, similar to how boiling water moves. Finally, this energy reaches the sun's outer layers and becomes the sunlight that warms our Earth. This nuclear fusion process not only keeps the sun glowing, but also sets the stage for forming heavier elements. When larger stars age, they fuse heavier elements, adding to the cosmic pool of elements essential for planets and life. So, nuclear fusion in the sun's core doesn't just generate energy. It's a fundamental cosmic engine with a universe-wide influence. Through star life cycles, fusion fosters element creation and dispersion, linking galaxies far away with our own atomic existence. This incredible energy conversion process shapes stars, propels their life cycles, and plants the seeds for an element-diverse universe. Sunspots are intriguing features on the sun's photosphere, known for their cooler temps and strong magnetic vibes. They usually show up as dark spots on the sun's bright surface and can range widely in size, with some stretching out tens of thousands of kilometers, big enough to swallow Earth whole several times over. Sunspots occur when powerful magnetic fields from inside the sun mess with regular convective processes, creating cooler surface areas around 4,000 degrees Celsius compared to about 5,500 degrees Celsius in nearby parts. The magnetic chaos linked with sunspots often triggers spectacular solar events like solar flares and coronal mass ejections. Solar flares are intense bursts of radiation due to magnetic energy release, causing dramatic flashes of light, radio waves, and high-energy particles. These flares can accelerate protons and electrons to nearly the speed of light, affecting space weather. Coronal mass ejections are even bigger, involving massive amounts of the sun's plasma being flung into space. When these charged particles head toward Earth, they can clash with our planet's magnetosphere, causing geomagnetic storms. These storms have countless effects on space weather, impacting everything from satellite ops to communication systems and power grids. High-energy solar flare particles can damage satellite electronics. When charged particles from CMEs hit Earth, they can stir up electric currents in power lines and pipelines, sometimes leading to outages and interruptions. But These same interactions are behind the stunning auroras, or the northern and southern lights, where particles excite gases in our atmosphere, crafting shimmering light displays. Grasping how sunspots influence space weather is vital in today's tech-driven world, offering ways to lessen impacts on our modern setups, while also shedding light on the dynamic dance between Earth and the Sun. Solar flares and coronal mass ejections, CMEs, are two potent forms of solar activity that affect Earth in both beautiful and risky ways. Solar flares are sudden, strong blasts of radiation from the Sun's atmosphere, driven by the complex dance of magnetic fields near sunspots. These flares send out a range of electromagnetic radiation, including X-rays and ultraviolet light, which reach us in just 8 minutes. When this happens, they can mess with the ionosphere, disrupting radio communications and navigation services like GPS, something crucial for aviation and maritime folk who rely on these systems for safe travels. Meanwhile, CMEs are huge blasts of solar wind and magnetic fields ejected from the solar corona into space. If they head toward Earth, they take a few days to arrive, while bringing along billions of tons of charged particles. Once they hit, these particles interact with Earth's magnetosphere, potentially setting off geomagnetic storms. Such storms can stir up electric currents in power lines, damaging transformers and causing widespread power grid failures, like the big Quebec blackout in 1989. CMEs can also harm satellites, leading to malfunctions or wear of their electronic bits due to intense particle radiation. Besides the tech issues, solar flares and CMEs also create mesmerizing auroras. When charged particles from these solar happenings crash into gases in the Earth's upper atmosphere, they light up the sky with the northern and southern lights. While mainly seen near the poles, these displays sometimes appear at lower latitudes during strong geomagnetic storms. Despite their beauty, the dual nature of solar flares and CMEs, as both potential technological threats and natural wonders, highlights the need for monitoring solar activity to protect our tech-integrated lives. The solar cycle, which lasts around 11 years, significantly affects solar phenomena and space weather. It's driven by the Sun's ever-changing magnetic field, which flips in polarity roughly every 11 years. The cycle kicks off with the solar minimum, where the Sun is calm, with few sunspots and minimal activity. As the cycle advances, reaching the solar maximum, sunspots multiply massively alongside frequent solar flares and CMEs. During this peak, the Sun buzzes with activity, often giving rise to new sunspots linked to strong magnetic fields. At this time, solar flares, more frequent than ever, can disrupt satellite communication, affect GPS, and interfere with power grids. Similarly, CMEs grow more common and forceful, leading to potentially severe geomagnetic storms when their particles meet Earth's magnetosphere. These storms can threaten technological infrastructure and increase radiation exposure for astronauts and those on high-altitude flights over polar areas. The solar cycle's ups and downs also wield a wider influence on space weather and conditions near Earth. When there's a solar maximum, the uptick in solar activity can make Earth's outer atmosphere swell. This means satellites could face more atmospheric drag, which might throw their orbits off and demand some tweaking. Plus, the ups and downs of the sunspot cycle decide how much ultraviolet and X-ray radiation hits Earth, impacting the ozone layer and the atmosphere's chemistry. Getting a handle on the solar cycle is key for predicting and getting ready for these solar waves, especially with cutting-edge observations from NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory. Thanks to these tools, scientists are better prepared to predict how the sun's changes might mess with our tech-dependent world. They use a mix of solar observatories, satellites, and spacecraft to dig into the sun, untangling the secrets of its behavior and effects on the solar system. Ground-based spots like the Daniel K. Inouye Solar Telescope in Hawaii give crystal-clear images of the sun's surface, letting researchers peek into sunspots, solar flares, and surface happenings. These telescopes are kitted out with fancy optics and tech to dodge Earth's atmospheric hiccups, giving scientists a peek at the magnetic fields and plasma waltzing on the sun's photosphere. Meanwhile, space-based telescopes and probes give views without the pesky atmospheric interference. Take NASA's Solar Dynamics Observatory, for example. It keeps an eye on the sun in different wavelengths, from extreme ultraviolet to visible light, showcasing the bubbling action in the sun's outer layers. The SDO snaps detailed shots of solar flares, sunspots, and magnetic changes, giving essential info to decode solar activity cycles and forecast space weather. Likewise, since 1995, the European Space Agency's Solar and Heliospheric Observatory has been a big help in shadowing the sun's atmosphere and catching early coronal mass ejections. Missions like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter step it up by heading close to the sun for up-close data. The Parker Solar Probe, launched in 2018, dives into the sun's outer corona, braving intense heat to measure magnetic fields, solar winds, and high-energy particles, hoping to unravel the solar corona's heating enigma and the solar wind mechanisms. Solar Orbiter, loaded with instruments, gets close to take high-res pics of the sun's poles, areas that were hard to study before. By combining data from all these sources, scientists can piece together a detailed and shifting picture of solar activity, aiding in forecasting and reducing the effects of solar events on Earth's tech scene and daily life. The moon's phases are like a magical play of light and shadow, transforming its look as it circles Earth, finishing a lap roughly every 29.5 days. This round, called a lunation, comes from the dance of positions between the moon, Earth, and the sun. As the moon makes its journey around Earth, different parts of its sunny side show up for us, crafting its phases. These phases break down into 8 main steps. It kicks off with the new moon when the moon is stuck between Earth and the sun. Here, the moon's side facing Earth is all shadow, making it vanish from the night sky. As it marches on, the moon hits the waxing crescent phase, where a little slice of its surface catches the sun's glow, forming a crescent. Night by night, this crescent grows until the moon arrives at the first quarter phase, often known as the half moon, with half of its disk lit up and visible from Earth. Then comes the waxing gibbous phase. Here, over half of the moon is shining, swelling up until it blossoms into a full moon. At this point, the moon stands directly across from the sun, with Earth nestled in between, letting us see the whole sunlit side of the moon. After the full moon, we move into the waning gibbous phase, when the light starts to fade. Next, we reach the last quarter, another half-moon phase, but with the opposite side lit up compared to the first quarter. The cycle winds down with the waning crescent, a thin sliver of light. before starting anew at the new moon. These phases highlight the graceful dance of celestial bodies. They're due to the angle of the moon's lit side as seen from Earth and the Sun. This ongoing shift gives us a natural rhythm in the night sky and has been important throughout history for keeping time and in cultural myths around the world. Knowing the moon phases helps us see the complex motions of celestial bodies and the ever-changing nature of our universe. The mystery of the moon's creation has intrigued scientists for ages, leading to different theories. The most accepted one is the giant impact hypothesis. This suggests the moon formed about 4.5 billion years ago after a huge collision between early Earth and a Mars-sized object called Theia. The impact was enormous, vaporizing Theia and part of Earth's mantle, sending debris into space. Eventually, gravity pulled this debris together to form the moon. This is backed by the moon's makeup, which is much like Earth's mantle, indicating shared origins. Other theories exist, but aren't as popular. Take the capture theory, for instance, which says the moon formed elsewhere and got caught by Earth's gravity, but it can't explain why Earth and the moon have such similar isotopic compositions. Then there's the fission theory, which suggests a fast-spinning Earth threw off a chunk of mantle that became the moon, but that would have needed incredible rotation speed. Another idea is the co-formation theory, proposing Earth and the moon developed together from the solar system's material, which doesn't explain the differences in their compositions. While the giant impact hypothesis is the frontrunner, it evolves with new findings and better computer models. Recent lunar rock analyses and simulations hint that multiple impacts may have played a role in forming the moon. Studying the moon's origins not only reveals early tales of Earth and its satellite, but also sheds light on the processes shaping planetary systems across the universe. The moon's surface is an incredible canvas of geological features that tell the tale of dynamic celestial events. Among the most captivating features are the lunar maria, or seas, created by ancient volcanic activities. Despite the name, these seas are basaltic plains formed billions of years ago from cooling lava. Some notable maria, like Mare Tranquillitatis, Sea of Tranquility, and Mare Imbrium, Sea of Rains, are visible to the naked eye, marked as dark spots on the moon. In contrast, the lunar highlands are lighter and more crater-dense, constituting the moon's more ancient regions. These highlands bear craters of various sizes, evidence of the moon's violent encounters with meteoroids and asteroids. The largest crater, the South Pole Aitken Basin, stretches about 2,500 kilometers wide and dives 8 kilometers deep, making it one of the solar system's largest impact sites. Famous craters like Tycho and Copernicus have noticeable central peaks with bright rays extending across the lunar landscape. Also intriguing are lunar rills, long, narrow grooves resembling channels or valleys that can stretch hundreds of kilometers. What you're seeing are thought to be pieces left over from old lava flows or where lava tubes broke down. The moon also has these steep cliff-like things called scarps, hinting at some tectonic stuff going on, even though it doesn't have the active plate tectonics like Earth does. Scarps found in areas like Rupes Recta, or the Straight Wall, show that the moon's insides are still cooling down and shrinking, which makes its crust crack and move around. Then there's the moon's surface layer, known as regolith, which is just a bunch of rocky bits and dust built up over millions of years from tiny meteoroid hits. This dusty stuff sits on top of the moon's solid layer, giving it a uniquely rugged and interesting look. The mix of maria, highlands, craters, rills, scarps, and the ever-present regolith combine to craft the moon's fascinating geological story, a quiet testament to the vibrant processes shaping our nearest neighbor in space. The moon has a big job in controlling Earth's tides, all thanks to its gravitational pull. This pulling and tugging between Earth and the moon sets up tidal forces that make ocean levels swing up and down in a regular dance. Think of Earth as a giant ball wrapped in flowing water. The moon's gravity tugs on this water, causing a bulge we call the tidal bulge. On the side of Earth closest to the moon, the water stretches toward it, creating high tide. Meanwhile, on the opposite side, the Earth's turn makes a second bulge, causing another high tide. As Earth spins, different spots rotate through these bulges, getting high and low tides twice each day. Yet, it's a bit more tangled because of the positions of the sun, moon, and Earth, which can tweak the tide's intensity. When these three form a line during full or new moons, their joined forces amp up the tides, which are called spring tides, leading to very high and very low tides. Conversely, when the sun and moon form a right angle with Earth during the first and third quarters of the moon's cycle, it results in neap tides, which are not as intense. The moon's tug on the tides also affects the Earth in broader ways. Tidal movements help churn the ocean, spreading nutrients crucial for marine life. Tides also have had a historic role in helping humans with navigation, fishing, and choosing where to settle along coasts. Plus, the interplay of ocean tides and Earth spinning is like a cosmic break, slowly lengthening our days over geologic timescales. This dance of gravity and rotation showcases the moon's big yet often subtle role in the workings of our planet, intertwining Earth's cycles with its celestial buddy. The Apollo moon missions from 1969 to 1972 opened a wealth of scientific understanding and tech advancements, forever changing how we view the moon and space exploration. A major highlight was bringing back about 382 kilos of lunar rocks, soil, and core samples. These treasures, carefully studied back home, gave us crucial insights into the moon's makeup, history, and surface-changing activities. These studies showed the moon is mostly made up of silicate minerals, similar to Earth's mantle, which supports the idea that the moon's origin might be because of a gigantic impact. The Apollo missions also enabled astronauts to conduct direct geological explorations on the moon's surface, where they carried out experiments, set up scientific tools, and gathered samples from different places, such as the highlands and maria. This allowed scientists to stitch together a detailed geological timeline. They found evidence of volcanic activity and impact cratering, revealing how both internal and external forces have shaped the moon's surface. Setting up seismometers on the lunar module revealed moonquakes, giving scientists clues about the moon's interior. Though the moon doesn't have tectonic plates, the data hinted at its complex inner structure, with a crust, mantle, and small core. The Apollo missions were groundbreaking, making leaps in technology from spacecraft design to life support systems, and teaching us the ropes of space exploration. The tech they developed went far beyond space, impacting material science and computer tech, among other fields. These missions also promoted global teamwork and sparked interest in future scientists, engineers, and enthusiasts. Today, the legacy of Apollo continues to influence lunar exploration. The instruments and methods developed have paved the way for modern moon research. As we gear up to return to the moon with programs like NASA's Artemis, which aims to set up a long-term human foothold on the lunar surface, the wisdom from Apollo acts as a shining guide. These missions weren't just about human inventiveness. They solidified our cosmic curiosity and showed how exploration can lead to world-changing discoveries. The future of human exploration and settling on the moon is set to be revolutionary, driven largely by tech advancements, global partnerships, and ambitious space initiatives. A major player in this journey is NASA's Artemis program, which seeks not only to return humans to the moon by 2024, but also to establish a long-lasting presence by the decade's end. This program represents a daring move towards sustained lunar exploration, building on Apollo's successes with today's technology. Artemis the Fern, an uncrewed mission, will test the Space Launch System, SLS, rocket, and Orion spacecraft, setting the stage for future manned missions. Artemis II will conduct a crewed flyby, setting the pace for Artemis III, where astronauts will touch down at the lunar South Pole, a location rich in both water ice and research potential. Besides NASA, international bodies and the private sector are key players in this new chapter of lunar exploration. The European Space Agency, Russian Space Agency, and China National Space Administration have all laid out their lunar plans, keen to be part of the scientific and exploratory gains. The International Lunar Research Station, a project envisioned by China and Russia, represents this cooperative mindset, planning a research hub staffed by humans and robots. A vital component of lunar colonization will be advancements in situ resource utilization, or ISRU, which involves using the moon's natural resources like extracting water to create oxygen and fuel, essential for sustaining outposts and further missions. Infrastructure will focus on creating habitats to protect astronauts from the harsh lunar conditions, such as extreme temperatures and harmful solar rays. Exploring 3D printing using lunar soil for building these structures is already underway. Companies like SpaceX and Blue Origin are central to realizing lunar ambitions. SpaceX's Starship aims to transport sizable loads and crews to the moon, making launches more affordable and missions more extensive. Blue Origin's Blue Moon lander is designed for cargo and crew transportation, furthering lunar colonization goals. These collective efforts could turn the moon into a hub for science research, technology breakthroughs, and a launch pad for deeper space missions, like journeys to Mars. Having humans on the moon will provide critical experience in living and working beyond Earth, preparing us for a future across planets. The dream of the moon is no longer far off. It's becoming a reality that may transform our understanding of the solar system. Stars come in a mind-blowing range of sizes, colors, and types, each unfolding its own tale across the universe. On one end of the starry spectrum are the tiny but numerous red dwarfs. These little stars, often less than half the sun's mass, burn their fuel so conservatively that they can live for trillions of years, outlasting stars like our sun by far. With surface temperatures from 3,000 to 4,000 Kelvin, red dwarfs give off a cool, reddish glow. Their energy-saving ways and long lifespans stand in stark contrast to the heftier stars in the universe. When we look at our sun, it's a G-type main sequence star, often called a yellow dwarf. Despite sounding modest, the sun is actually bigger and brighter than many stars in the galaxy. Beyond it lie the enormous blue giants and the even bigger blue supergiants. Stars like Rigel and Betelgeuse in the Orion constellation shine bright with surface temperatures from 10,000 to over 30,000 Kelvin, beaming blue and white light. But their brilliance comes at a price. Blue supergiants burn through their nuclear fuel incredibly fast, cutting their lives short to just a few million years. As they reach their life's end, many go out in spectacular supernova explosions, leaving behind puzzling remnants like neutron stars or black holes, the ultimate cosmic mysteries. The birth of a star is like a symphony of cosmic forces in the dark, cold parts of space known as stellar nurseries. These nurseries are vast clouds of gas and dust, mostly hydrogen and helium, drifting quietly in galaxy arms. Over time, gravity makes chunks of these clouds collapse and stick together. As these chunks get denser, they grab more material and the core's temperature rises. This keeps up until the temperature hits about 10 million Kelvin. It's then that nuclear fusion kicks in, marking the arrival of a new star. It's amazing how the process begins so quietly with just tiny pulls of gravity and finishes with the roar of nuclear flames. As the new star gathers material, it often creates stunning visual scenes. Around the young star, leftover gas and dust make protoplanetary disks that might form planets. In places like the Orion Nebula, astronomers have captured the sheer beauty of these stellar beginnings, where thick pillars of gas and dust swirl around newborn stars lit by their new light. The mix of radiation pressure from these young stars and the gravitational tug-of-war creates intricate, short-lived structures in the nebula. The life journey of a star, is an epic cosmic tale unfolding over billions of years with dynamic transformations. It all kicks off in stellar nurseries, sprawling clouds of gas and dust peppered throughout galaxies. As gravity pulls these clouds inward, protostars form and eventually ignite nuclear fusion in their cores, turning into main sequence stars. This phase, where stars spend most of their lives, involves a delicate balance between gravity pulling inward and the outward push from nuclear fusion. Our Sun, for instance, has been in this stable phase for around 4.6 billion years and will stay this way for another 5 billion years. As stars burn through their hydrogen fuel, their fates split based on their initial mass. Stars about the size of the sun balloon into red giants. In this blown-up state, their outer layers are shed, forming beautiful planetary nebulae, leaving a dense, hot core known as a white dwarf behind. These white dwarfs gradually cool and fade away over billions of years. In contrast, massive stars meet more dramatic ends. After burning through heavier elements like helium, carbon, and eventually iron, their cores collapse under gravity's fierce pull, sparking supernova explosions. This explosive event can temporarily outshine entire galaxies, scattering enriched material back into space, setting the stage for future stellar generations. When the massive stars reach the end of their lives, what's left can become incredibly dense neutron stars, or, if large enough, they might collapse down further into mysterious black holes. These cosmic phenomena have gravity so strong that even light can't break free. So, the story of a star's life is pretty fascinating. It's full of creation, change, and sometimes dazzling destruction, all of which help the universe evolve. Supernovae, those massive explosions marking the end of a star's life, aren't just about destruction. They also kickstart new cosmic beginnings. When a supernova goes off, it throws out a huge amount of energy, scattering the outer layers of the star into space. This material is packed with heavy elements like iron, oxygen, and silicon, created through nuclear fusion in the star's core. These clouds, known as supernova remnants, distribute these crucial elements throughout the galaxy, elements that were once trapped inside the star. The shock wave from the supernova stirs things up too, playing a big part in forming new stars. As it sweeps through space, it compresses nearby gas and dust, creating zones that might collapse to form new stars. This acts like a cosmic jumpstart for star formation in nearby galaxy regions. Places with lots of supernova leftovers become hotspots for new stars. Take the Orion Nebula, for example. It shows this beautifully, teeming with remnants of old stars while new ones light up. This ongoing cycle of life and death, fueled by supernova, keeps the universe's story vibrant and ever-changing, where one star's end plants the seeds for many new ones. Black holes might sound like terrifying space monsters, but they are the mysterious remnants of some huge stars. These black holes come to be from the intense final phases of a star's life, particularly through a supernova's grand finale. When a star more than 20 times the mass of our Sun runs out of nuclear fuel, gravity gets the upper hand. The star's core collapses, compressing its matter into something called a singularity, an infinite density point. It all starts when the star's core collapses inward, where protons and electrons combine to form neutrons, which is what creates a neutron star in the right conditions. But for the really big stars, even this doesn't stop the collapse. The core keeps shrinking till it becomes a black hole, an area where gravity is too extreme for even light to get out. Around this singularity is the event horizon, the no-turning-back point. Anything that crosses this boundary gets drawn into the black hole. Although they're often seen as menacing, black holes are vital to the cosmic order, influencing galaxy formation and bending the space-time fabric. Their existence was hinted at by equations of general relativity in the early 1900s, but it wasn't until later advances in tech that we had proof they were real. Nowadays, things like gravitational waves picked up by LIGO give us direct evidence of black hole mergers, confirming their place in the universe's grand symphony. So, from a massive star's death, out comes something deeply fascinating. A black hole, continuing the endless dance of destruction and creation across space. Then, there are binary star systems, where two stars orbit their common center of mass, offering a compelling stage to explore stellar dynamics and evolution. In these unique setups, the stars are locked in a celestial tango, with each star's motion influenced by the other's gravitational pull. This gives astronomers a natural lab to test ideas about star physics, as their interactions reveal insights into their masses, makeups, and lifespans that might otherwise stay unknown. The paths they travel around their shared center can be pretty varied and intricate. Some binary star systems have circles that are nearly perfect, while others have eccentric paths, causing the stars to pull close and then drift apart in a steady rhythm. These orbital differences actually influence how stars change as time goes by. In systems where the stars are really close, their gravity pulls can cause one star to pass material to the other, which dramatically shifts how they both evolve. Take, for example, a red giant star sharing its outer layers with a smaller star. This can lead to the giant shrinking into a white dwarf and might even ignite a nova if the transferred material lights up. In some situations, this closeness can result in dramatic cosmic events like the emission of gravitational waves or even the merging of stars, deepening our grasp of stellar behavior. Things get extra interesting when a star in a binary system turns into a dense object like a white dwarf, neutron star, or black hole. These dense remnants can pull in matter from nearby stars, forming disks that emit strong X-rays that we can spot from Earth. A well-known example is the Cygnus X1 system, which features a stellar black hole with a companion star, providing some early strong evidence for the existence of black holes. Binary star systems, with their wide range of actions and unusual interactions, not only put on fascinating cosmic shows, but also become essential tools for exploring the universe's fundamental laws. Constellations are intriguing star groups that people have identified and named for thousands of years. These star formations have been a backdrop for countless myths, stories, and legends across cultures from ancient Babylon to Greece and around the globe. They have historically helped humans organize the night sky and track celestial movements. Unlike groups held together by gravity, constellations are simply how we see stars from our viewpoint on Earth, functioning like a celestial map that's been guiding human exploration of the stars. In the past, constellations had substantial practical and cultural value. Sailors depended on formations like the Big Dipper, part of Ursa Major, for sea navigation, using star positions for determining their locations. Farmers also used them to track seasons, identifying when certain constellations appeared to decide when to plant or harvest crops. Beyond daily uses, constellations played a big role in cultural and religious practices. Greeks, for instance, embedded tales of their gods, heroes, and myths into the stars, with stories like Orion the Hunter and his loyal dogs, Canis Major and Canis Minor, forever pursuing the celestial hare, Lepus. In modern times, astronomy has classified 88 constellations, setting boundaries to help with scientific study and cataloging celestial bodies. The International Astronomical Union, or IAU, established these borders in the 20th century, making sure every segment of the sky is part of a specific constellation. Even now, constellations continue to inspire and educate, acting as memory aids to locate stars, nebulae, and galaxies. Through the combined views of history and science, constellations show humanity's deep need to make sense of the universe and seek meaning in the stars. Among the broad expanse of stars twinkling at night, some constellations are prominent for their unique shapes and the rich stories linked to them. Consider Orion, one of the most easily recognized because of its three-star belt. In Greek myths, Orion was a great hunter, known for his looks and skills that even attracted the attention of the gods. This ultimately led to his downfall by either a giant scorpion's sting, now the constellation Scorpius, or other tales of divine punishment. Whatever the myth details may be, Orion's legendary story continues to fascinate people everywhere. Another constellation with a rich history is Ursa Major, also known as the Big Dipper in the Northern Hemisphere. The 7 bright stars making up the Big Dipper are part of a larger formation that looks like a big bear. In Native American legends, the Big Dipper is seen as a sky bear being chased by 3 hunters, a story that has been passed down over many generations. The Greeks had their own version. They saw Ursa Major as Callisto, a nymph who was turned into a bear by Hera due to jealousy. Then Zeus placed her among the stars. Her son Arcas became Ursa Minor, and together these constellations represent transformation and family bonds in the sky. Cassiopeia, with its famous W shape, represents a queen whose conceit was her undoing. According to Greek lore, Cassiopeia boasted about being more beautiful than the Nereids, the sea nymphs close to Poseidon. In response, Poseidon punished her by putting her in the sky, where she eternally spins around the celestial pole, often upside down, as a warning against vanity. These constellations, along with others like Pegasus, Andromeda, and Leo, create an intricate web of stories that blend culture, observation, and the age-old art of storytelling, cementing their place in both astronomy and myth. The Milky Way, our cosmic home, is a grand spiral galaxy full of stars, gas, dust, and dark matter arranged into several key parts. At the center, there's a region filled with a supermassive black hole called Sagittarius A, weighing about 4 million times more than our Sun. Around this chaotic core is the galactic bulge, packed with old stars and star clusters that stretch thousands of light years across. Extending from the bulge are the galaxy's signature spiral arms, known for their sweeping curves and active star formation. Our solar system hangs out in the Orion Arm, a smaller branch between the bigger Perseus and Sagittarius arms. These arms are full of young stars and interstellar stuff, providing a sparkling backdrop of star nurseries and nebulas. The spiral form stays intact thanks to density waves that pass through, compressing gas and sparking new stars. Surrounding the spiral arms is the galactic disk, a flat, rotating plane with most of the galaxy's stars and nebulae. This disk is surrounded by a vast halo of old stars and globular clusters, some of the oldest objects we know. The halo is thought to be full of dark matter, that mysterious stuff that exerts gravity without shining light, affecting the galaxy's overall mass and motion. Beyond lies the outer zone of the galaxy, where lone stars and faint star streams, remnants of past mergers, drift in a scattered void. The Milky Way's vibrant structure tells a story of numerous interactions with other galaxies, shaping its path over billions of years. This grand spiral city of stars, stretching over 100,000 light-years wide, is home to countless star systems like our own, weaving the complex tapestry of our galaxy's character. Galaxies, the enormous structures in our universe, come in several shapes and sizes: spiral, elliptical, and irregular. Each kind gives us clues about how cosmic structures form and grow. Spiral galaxies, like our Milky Way, are striking with their winding arms spreading from a central hub. These arms are bustling star factories where hot, blue stars are born, enhancing the spiral's look. Spiral galaxies can also have a bar across their center or not, splitting them into different types. The star mix within spirals varies, with older, red stars mainly in the center and younger ones scattered through the arms. The defined structure hints at rotation and a wealth of gas and dust needed for making new stars. Elliptical galaxies, on the other hand, have a more uniform, oval shape and don't have the complex layout seen in spirals. Elliptical galaxies come in various shapes, from nearly perfectly round to super stretched, and they're mostly filled with older red stars. This old star crowd indicates these galaxies have used up a lot of their interstellar gas, leaving little for new star births. As a result, they're generally quieter and less lively compared to spiral galaxies. Scientists believe elliptical galaxies come about when smaller galaxies crash into and merge with each other, messing up their initial form and leading to the smooth appearance they have now. Meanwhile, irregular galaxies don't fit neatly into any category and don't really have a clear shape. They're usually smaller than their spiral and elliptical peers and often look disordered, with areas of new star creation mixed with spots of older stars. This messiness might come from gravitational tugs of nearby galaxies or leftover chaos from galactic smashes. The wide variety of their looks tells a story of a rocky past, and they usually have a lot of gas and dust, which keeps new stars forming. Spiral, elliptical, and irregular galaxies highlight how diverse cosmic structures can be. Spiral galaxies, with their stunning arms and bustling new star creation, elliptical galaxies with their peaceful, older stars, and the unpredictable irregular ones all add to the universe's rich variety, showing off different galactic shapes and backstories. In the universe's vastness, some galaxies are absolutely huge, overshadowing even the Milky Way. Among these giants, IC 1101 is the biggest known galaxy, a massive elliptical beast over 1 billion light-years away in Virgo. This galaxy stretches an astonishing 6 million light-years across, about 60 times wider than the Milky Way, housing countless old, red stars, indicating it's no longer sparking new stars to life. Its massive size results from billions of years of galaxy mergers, gaining size and mass through gravity's pull. There's also the impressive ESO 30617, another elliptical galaxy about 500 million light-years away. Though not as enormous as IC 1101, it's still impressive at over 1 million light-years wide. The discovery of many globular clusters around such big elliptical galaxies hints at their complex and chaotic formative past, often marked by frequent mergers and nearby galaxy interactions. Further exploring these cosmic giants is the galaxy cluster Abell 2029, anchored by the large elliptical galaxy NGC 6166. Though not as grand as IC 1101, NGC 6166 is fascinating because of its huge central black hole and strong radio waves. It serves as the center of a massive galaxy cluster, playing a big role in its gravitational influence and the complex galaxy cluster dynamics. By studying these enormous galaxies, astronomers get crucial insights into how galaxies grow, how dark matter shapes them, and what happens when galaxies merge. Each giant tells a tale of the endless creativity and complexity of the universe. The journey of galaxy formation and growth is a mix of intriguing events stretching over billions of years. It all starts soon after the Big Bang, when the early mix of hydrogen and helium cools. Tiny density variations in this otherwise even universe give gravity a chance to pull stuff together, forming the first proto-galaxies and stars within what we now call the cosmic web. In these early times, little clumps of gas and dark matter clump under gravity's force to create the first tiny galaxies, acting as seeds for bigger structures. Over time, through crash-ups and gathering, these small galaxies blend into larger ones. This tiered structure plays a key role in the lambda cold dark matter cosmological model, explaining how galaxies grow and change over time. Interactions and mergers don't just boost a galaxy's mass, they also mix up the gas inside them. This often leads to star bursts or sudden flashes of star formation. A galaxy's form can also shift significantly after such mergers. For instance, when spiral galaxies crash into each other, they often morph into elliptical galaxies because the crash disrupts their neat, disc-like forms into more rounded shapes. On the flip side, spiral galaxies, like our Milky Way, usually hang out in less crowded areas, which helps them keep their spiral shapes since they have fewer collisions. As galaxies grow and interact, they also change due to internal processes. Spirals can continue creating stars for billions of years, turning interstellar gas into new stars. But when the gas dries up, star production slows and the galaxy ages, shifting from a young blue spiral into a calmer, redder form with older stars. Supernova blasts and the activity of supermassive black holes at the centers of galaxies are crucial too. They help control star formation and spread out gas. All in all, the life of a galaxy is a tale of constant formation, growth, and change, sometimes through dramatic encounters. From the quiet, dark origins of the early universe to the intricate, bright formations we see now, galaxies' journeys display the complex cosmic forces that shape our universe. Dark matter and dark energy are mysterious parts of the cosmos, with a big impact on how galaxies form and evolve, even though they're hard to pin down. They make up about 85% of the universe's matter, but dark matter doesn't emit, absorb, or reflect light, staying invisible to regular observation methods. Dark energy composes roughly 70% of the universe's energy content and is believed to drive the cosmos's accelerated expansion. In galaxy formation and structure, dark matter acts like the framework on which galaxies form. In the early universe, areas with slightly more dark matter became gravitational pulls that attracted normal matter, leading to proto-galaxies. Dark matter halos, spherical spreads of dark matter around galaxies, offer the gravitational force needed to hold galaxies together. Observations of galactic rotation curves, where outer galaxy regions spin faster than we'd expect based on visible matter, strongly suggest these dark matter halos exist. Without dark matter, galaxies wouldn't have enough gravity to keep stars, gas, and dust from flying off. Dark matter also affects galactic interactions and mergers. When galaxies collide, their dark matter halos can pass through each other almost untouched, as dark matter mostly interacts through gravity, not electromagnetically. This behavior can ramp up the rate of galactic mergers, which influences the final shapes and sizes of the merged galaxies. The largest things in the universe, like galaxy clusters, owe their existence to dark matter's gravitational pull, sticking hundreds or thousands of galaxies together. Dark energy, meanwhile, plays a somewhat different but still significant role. It's thought to drive the universe's accelerated expansion, noted through studies of far-off supernovas and cosmic microwave background radiation. While this expansion might seem like a broader influence, it subtly affects galaxies. As the universe expands faster, galaxies' gravitational attraction weakens, making future mergers and encounters less probable. Dark energy plays a key role in shaping the universe's galaxy and void layout on a large scale. To truly grasp the structure of the cosmos, dark matter and dark energy are crucial. Dark matter forms the backbone that keeps galaxies intact, while dark energy leads the universe's expansion journey. Together, they guide the complex movements of galaxies, influencing the universe on a small and vast scale. The Andromeda Galaxy, or M31, is a standout feature in the Milky Way's nearby cosmic setting. It's roughly 2.5 million light-years away, making it the closest spiral galaxy to ours and one of the largest in the local group, which has about 54 galaxies, including the Milky Way. Andromeda is noteworthy for several reasons, especially its looming collision with the Milky Way, a future event that will greatly affect both galaxies' structures. Andromeda is a bit bigger than the Milky Way and holds over 1 trillion stars, compared to our galaxy's 200 to 400 billion estimate. Its mass gives Andromeda a strong gravitational pull within the local group. One compelling aspect of the Milky Way and Andromeda's bond is their impending collision. Due to their gravitational pull on each other, they're closing in at about 70 miles per second. This massive event, expected in 4.5 billion years, will probably blend the two into one large elliptical galaxy, often called Milkomeda or Milkdrameda. Though dramatic, the collision isn't something to dread, as the vast space between stars means actual star collisions will be rare. Instead, gravitational forces will lead to an amazing change. The spiral forms of both galaxies will break down, and their central black holes might eventually merge, creating gravitational waves detectable across the universe. Such galaxy mergers are common and play a critical role in galaxy evolution. Besides its involvement in this future cosmic event, Andromeda offers astronomers a valuable comparison for studying how galaxies form and evolve. Its proximity allows for detailed observations that help scientists learn about star formation, galaxy dynamics, and the life cycle of galaxies. Comparing Andromeda and the Milky Way reveals how outside factors and inner processes can shape the fate of spiral galaxies. Andromeda acts both as a reflection and a partner to the Milky Way, highlighting the complex and dynamic nature of galaxy interactions. Its eventual merger with our galaxy serves as a reminder of the constantly shifting, interconnected fabric of the universe, showing us that even on a grand scale, nothing stays the same, instilling in us both awe and anticipation for what's ahead. Galaxy collisions are major cosmic events that greatly influence the universe's structure and evolution. These striking encounters have wide-ranging effects, impacting not only the galaxies involved, but also the larger cosmic environment. When galaxies collide, their gravitational forces play a complex role, affecting star formation, the growth of supermassive black holes, and the shapes of resulting galactic structures. In the early stages of a collision, galaxies don't crash together like solid objects, but instead move through one another, with their stars, gas, and dark matter interacting through complex gravity. These interactions can spark bursts of star formation as gas clouds are squeezed and star nurseries ignite. This bright starburst phase is evident in colliding galaxies like the antennae, where bursts of new stars illuminate interaction zones. These starbursts can sometimes create dozens or hundreds of stars at once, greatly affecting the brightness and evolution of merging galaxies. As the collision advances, the original galaxy shapes get twisted, with tidal forces stretching and bending them into new forms. When galaxies come together, they can throw off long starry streams, known as tidal tails, into the vastness of space, like what we see in the famous mice galaxies. These cosmic encounters continue as galaxies weave through each other repeatedly, merging their hearts over time. This ongoing gravitational dance shakes up the neat structure of spiral galaxies, often turning them into elliptical ones. As their central supermassive black holes unite, they can send out powerful gravitational waves, fueling bright quasars or active galactic nuclei that outshine all the stars around them. On a bigger scale, galaxy collisions matter a lot. They back up the idea that smaller galaxies have been teaming up over billions of years to form the larger ones we see today, from graceful spirals to shapeless ellipticals. Within galaxy clusters, these collisions shuffle around dark matter, gases, and the overall balance of the cluster. What's left after the collision, new galaxies and cast-off stars and gas, enriches space with elements crafted inside stars, setting the stage for new stars to form and keeping the cosmic cycle going. These galaxy pileups are game changers, sparking new stars, changing galactic shapes, and helping supermassive black holes grow. They highlight how the universe is constantly evolving as galaxies keep interacting and changing, weaving a never-ending story of cosmic creation. Black holes, those fascinating enigmas in space, are spots where gravity is so intense that nothing, not even light, can escape. These mysterious objects form when massive stars, about 20 times bigger than our Sun, run out of fuel and collapse under their own weight. This collapse squeezes the core until density and gravity hit unimaginable levels, creating what's known as a singularity. Surrounding this singularity is the event horizon. Once crossed, there's no turning back, making black holes invisible to direct observation. Tracking down black holes might sound impossible, but scientists have come up with several clever tricks. One key method is observing nearby stars and gas. If a star orbits around something unseen, astronomers can guess there's a black hole influencing its path. They also look for X-rays coming from the hot, luminous material spiraling into a black hole just before it vanishes past the event horizon. And thanks to breakthroughs in gravitational wave astronomy, places like LIGO and Virgo now let us tune into the ripples in space-time caused by merging black holes. With these techniques, black holes, once elusive and puzzling, are now some of the best understood mysteries in space. The event horizon stands out as one of the most intriguing aspects of black holes. It's the boundary around a black hole, beyond which nothing, no particles, light, or information, can escape due to the extreme gravitational pull. This pull is so strong that once anything crosses this threshold, it gets pulled in towards the singularity, lost to the universe forever. To imagine how the event horizon works, think of space as a stretched-out fabric. When objects with mass bend this fabric, those bends represent gravity. A black hole is so massively dense that it bends space-time into a steep pit, kind of like a hole in space. The event horizon is the boundary of this pit. Just beyond this limit, to escape the black hole's pull, you'd have to travel as fast as light. Cross over the event horizon, and the required escape speed is even faster than light, meaning nothing can escape. This idea opens up fascinating questions in physics and information theory, sparking debates about what happens to information that falls into black holes and what matter becomes inside them. The event horizon isn't a solid thing. It's more like an invisible line where our usual physics, mainly based on general relativity, starts to stretch and twist. There are three main kinds of black holes, each with its own origin story and mass. The first, stellar black holes, are the most common, forming when massive stars, about 20 times the size of our Sun, exhaust their nuclear fuel and collapse under gravity. These black holes usually have a mass of a few to a few dozen times that of the Sun. Then there are supermassive black holes residing in the heart of most galaxies, including our Milky Way. These giants are as heavy as millions or even billions of suns. Despite their great size, how they form is still hotly debated. Some theories suggest they come from merging smaller black holes, while others think they quickly gather gas and stars early in the universe. They play a huge role in shaping their galaxies, influencing star formation and the galaxy's shape. Lastly, we have the intermediate mass black holes, hard to find and slightly mysterious, with masses between 100 and 100,000 suns. Finding strong proof of their existence is tricky, but they likely form through the merger of smaller black holes or from the collapse of big gas clouds. Understanding these could provide clues on how black holes grow and evolve, connecting the dots from stellar to supermassive black holes. Each type of black hole, with its own traits and origins, highlights how complex and dynamic our universe is, offering layers of cosmic puzzles that continue to captivate scientists. Now, imagine a neutron star, one of the universe's densest things, born from a supernova explosion. It's like an atom's nucleus squashed into a ball only about 12 miles wide, but with 1.5 to 2 times the mass of the Sun. This happens when a hefty star, 8 to 20 times heavier than the Sun, runs out of nuclear fuel and collapses. Initially, the star's core falls inward due to gravity, while its outer parts are blown away in a supernova explosion. What goes on in the core involves intense physics. As it collapses, protons and electrons are crushed together, forming neutrons under the intense pressure. This dense core stabilizes as a neutron star, so dense that a sugar cube-sized piece would weigh as much as all humans combined. Neutron stars have powerful magnetic fields and spin incredibly fast. Sometimes they appear as pulsars, these spinning neutron stars that shoot beams of electromagnetic radiation from their magnetic poles. They're fascinating endpoints in a star's life, but they also raise even more questions. These cosmic bodies act as natural experiments, offering insights into extreme physics. Take the inside of a neutron star, for example. What's in there is a hot topic for scientists, bringing together fields like quantum mechanics and general relativity. Studying these dense remnants sharpens our understanding of basic forces and how matter behaves at densities way beyond what we know on Earth. Among these are pulsars and magnetars, specialized kinds of neutron stars that show off an amazing variety of behaviors. Pulsars are stars that shoot out beams of radiation from their magnetic poles. As they spin, assuming their magnetic and rotational axes aren't lined up, the radiation sweeps through space like a lighthouse. If one of these beams hits Earth, We see it as regular radiation pulses, which is why they're called pulsars. These pulses are incredibly precise, happening every few milliseconds to seconds, making pulsars some of the universe's most accurate natural clocks. They're so reliable that scientists use them to test key physics principles, like general relativity. Then we have magnetars, taking the spotlight as neutron stars with insanely strong magnetic fields, thousands of times more intense than those of normal neutron stars or even pulsars. These fields are about a quadrillion times stronger than Earth's. Magnetars tend to spin slowly compared to pulsars, with rotations lasting seconds to minutes. Their intense fields lead to wild surface activity and explosive outbursts, showing up as strong bursts of X-rays and gamma rays. These can affect the star's crust, made of ultra-dense, neutron-rich material, causing starquakes and more energy bursts. Both pulsars and magnetars highlight the different traits in neutron stars. Pulsars help us explore space with their clock-like precision, while magnetars push the limits of our understanding of magnetic fields and high-energy events through their explosive emissions. They both give us unique insights into the extreme environments and fundamental physics involved in these dense remnants from supernovae, expanding our knowledge of the universe's strangest objects. Among the many black holes and neutron stars out there, a few stand out due to their unique features, historical significance, or groundbreaking science. Take Cygnus X1, one of the most famous black holes, located about 6,000 light-years from Earth in the Cygnus constellation. Found in the early 1970s, it was one of the first strong black hole candidates. This system has a blue supergiant star paired with a compact black hole, known for its powerful X-ray emissions as it pulls in matter from the supergiant. The discovery of Cygnus X1 was crucial in making the idea of black holes a reality in astrophysics, showing they exist beyond just theory. In neutron star lore, the Crab pulsar is legendary. It sits at the center of the Crab Nebula, a relic of a supernova blast seen by Chinese astronomers in 1054 AD. The Crab pulsar spins 30 times each second, sending out radiation pulses in different wavelengths, such as radio waves, light, X-rays, and gamma rays. It's a goldmine of information about pulsar wind nebulae, magnetic fields, and supernova remnants. Watching it across different parts of the electromagnetic spectrum makes it a key player in multi-wavelength astronomy. And then there's Sagittarius A, the huge black hole in the middle of our Milky Way. It's invisible to optical telescopes, but its presence is clear from the quick orbits of nearby stars circling an unseen behemoth with massive gravity. Using radio and infrared techniques, astronomers trace these star orbits to confirm Sagittarius A has an impressive mass, around 4 million times that of our Sun. Discovering and researching Sagittarius A has given us crucial insights into supermassive black holes and their impact on how galaxies form and change over time. Meanwhile, PSR B1919 is historically significant as it was the first pulsar found. Jocelyn Bell Burnell and Anthony Hewish discovered it in 1967, and its regular radio pulses first made people wonder about alien life until they realized it was a rapidly spinning neutron star sending out beams of radio waves. This groundbreaking find ushered in a new era for observational astrophysics, offering fresh ways to explore the extreme physics that govern neutron stars. Far from being just cosmic curiosities, these renowned black holes and neutron stars are key to expanding our knowledge of stellar evolution, gravitational theory, and the extreme conditions of matter, constantly pushing the limits of what we know in modern astrophysics. The Big Bang Theory stands as the leading model explaining how the universe started. It suggests that about 13.8 billion years ago, the universe began from a super hot, dense state and has been stretching out ever since. Importantly, the Big Bang wasn't an explosion in the typical sense, but an event that marked the beginning of space, time, and all existing matter and energy. The term Big Bang, initially jokingly used by British astronomer Fred Hoyle, has become the widely accepted name for this model. Multiple pieces of evidence back up the Big Bang theory. One of the strongest pieces of evidence is cosmic microwave background radiation, accidentally discovered by Arno Penzias and Robert Wilson in 1965. This faint glow throughout the universe is seen as the Big Bang's afterglow, offering a snapshot of the early universe when it was a mere 380,000 years old. The radiation is surprisingly uniform, with tiny variations that match the seeds of all present-day cosmic structures, like galaxies, stars, and planets. Another supporting evidence is galaxies' redshift, first described by Edwin Hubble. He noted that galaxies seem to be moving away from us, with their light shifting towards the red part of the spectrum, showing that space itself is expanding. This observation fits well with the predictions of general relativity that Albert Einstein developed earlier in the 20th century. Rolling the clock backward, this expansion suggests that the universe used to be much more compact. Additionally, the existence of light elements like hydrogen, helium, and tiny amounts of lithium, predicted by Big Bang nucleosynthesis, also backs this theory. These elements formed in the universe's first few minutes when conditions were hot and dense enough for nuclear reactions, creating these initial elements in amounts that align with what we see today. The Big Bang theory offers a detailed framework for understanding the universe's origin and its evolution over time. It explains both current observations and guides new discoveries, boosting our understanding of the cosmos as it changes over billions of years. Figuring out the universe's age and size involves combining observational astronomy, theoretical physics, and complex math models. A key method for measuring its age involves studying the cosmic microwave background radiation, CMB, the universe's oldest light. This radiation from the Big Bang, first found by Arno Penzias and Robert Wilson in 1965, provides a direct view into the early universe. By examining slight fluctuations in the CMB, scientists can deduce essential cosmological details, like the universe's expansion rate, known as the Hubble constant. Observatories such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have given precise readings of these fluctuations, resulting in the most accurate age estimates of the universe. Current data indicates the universe is about 13.8 billion years old. Another method studies the oldest star clusters, like globular clusters, which are tightly packed gatherings of ancient stars that provide a lower age limit for the universe. When astronomers figure out how old the oldest stars in clusters are, using what they know about how stars evolve and make new elements, they can confirm and tweak the age estimates they get from cosmic microwave background, CMB data. These stars are as old as we expect if the universe is billions of years old, backing up the findings from cosmic background studies. Figuring out the universe's size, especially the part we can see, is linked with understanding how it's grown over time. Edwin Hubble spotted that galaxies are moving away from us, and the farther they are, the faster they go. This observation was crucial in estimating the universe's scale. The Hubble constant, which defines how fast this expansion is happening, is key to measuring distances in space. Modern techniques using type Ia supernovae, which have a well-known brightness, help fine-tune the Hubble constant. Additionally, baryon acoustic oscillations, BAO, which are regular ripple-like changes in the density of visible matter, are another measure for cosmic distances. By combining the Hubble constant with the universe's age today, scientists can calculate the size of the observable universe. Because light takes time to travel, looking out into space is like looking back through time. So, the universe we can see is like a sphere around us, about 93 billion light-years in radius. It's larger than you'd think from just multiplying the universe's age by the speed of light, because space keeps expanding. Through combining these methods, studying the CMB, star clusters, supernovae, and cosmic growth, scientists piece together the story of the universe's immense age and size, shedding light on the observable cosmos and its dynamic past. Cosmic background radiation, or more officially, the cosmic microwave background, is like a glow left over from the Big Bang. It's a faint microwave signal filling up the universe. It was accidentally found by Arno Penzias and Robert Wilson back in 1965. The CMB is the leftover heat from the explosion that started everything. This radiation dates back to around 380,000 years after the Big Bang, when the universe cooled down enough for protons and electrons to join up and form neutral hydrogen atoms. This made the universe see-through and let light travel freely for the first time. Essentially, the CMB is a picture of the universe as a baby. Its importance to cosmology is huge. Primarily, it gives solid evidence for the Big Bang theory. Its nearly perfect uniformity, with tiny temperature variations of about 1 part in 100,000, matches what we expect from the Big Bang's predictions about the early universe being similar in all directions and locations. These small changes matter. They were the seeds for all the current structures in the universe, like galaxies, stars, and planets. They show areas with slightly different densities, which developed over billions of years into the cosmic structures we see now. Detailed CMB data, especially from missions like WMAP and the Planck satellite, have provided a wealth of cosmological info. These observations help refine key cosmological numbers, like the Hubble constant, the universe's growth rate, and the densities of regular matter, and dark energy. By carefully analyzing the CMB, scientists can also determine the universe's age very accurately, currently estimated at about 13.8 billion years. Plus, the CMB has revealed signs of cosmic inflation, the universe's rapid expansion right after the Big Bang. The patterns of temperature and polarization in the CMB give weight to this model, offering insights into the universe's earliest moments. These studies open doors to understanding fundamental physics at energy levels far beyond what we can achieve with particle accelerators on Earth. Cosmic background radiation stands as a critical cosmic relic, a faint echo of the universe's explosive beginnings and its evolution. A detailed map of the early universe helps us make sense of the cosmos from its beginning to the vast structured form we see today. It's a key source for both current and future astrophysical research. To study the universe's expansion, scientists mainly look at distant galaxies and the light they send out. A basic method they use is observing the redshift of light, a concept Edwin Hubble explored systematically in the 1920s. Redshift happens because as galaxies get further away due to the universe's expansion, their light gets stretched, moving it toward the red part of the electromagnetic spectrum. This shift is measured through spectroscopic techniques by comparing the absorption or emission lines in a galaxy's spectrum with those known in laboratories. The degree of redshift is directly related to the galaxy's speed and distance, helping us understand how fast they're moving away and revealing the universe's expansion rate. A crucial tool in this is the Hubble constant, denoted as h0, which describes how quickly the universe is expanding. This constant comes from Hubble's law, stating that a galaxy's velocity, v, directly correlates to its distance, d, from us, with h0 as the proportionality constant, v h0 xd. To measure the Hubble constant, precise distance measurements to galaxies are needed, which astronomers achieve through various techniques. One main method involves using standard candles, like type Ia supernovae. These supernovae have a uniform intrinsic brightness, allowing their distance to be calculated by comparing their known luminosity to how bright they appear. By plotting these distances against the redshifts of supernovae, scientists improve the accuracy of the Hubble constant, thus refining our knowledge of expansion rates. Another important research avenue is the study of cosmic microwave background, CMB, radiation. The CMB is the Big Bang's afterglow, mostly uniform in all directions with tiny temperature fluctuations that hint at the universe's early conditions. Space missions, such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have measured these fluctuations with great precision. Analyzing the CMB helps identify various cosmic parameters, including the universe's shape and its expansion rate over time. These findings support measurements obtained from galaxies and supernovae, forming a comprehensive picture of how the universe has grown. Moreover, scientists use baryon acoustic oscillations, BAO, as another standard ruler for measuring cosmic distances. BAO refers to periodic changes in the density of visible matter because of sound waves traveling through the early universe, which left a mark on the large-scale distribution of galaxies. By measuring the BAO scale in galaxy distribution, astronomers can further refine distances needed to calculate the universe's expansion rate. The study of the universe's expansion involves a mix of approaches, combining observations of distant galaxies, supernovae, cosmic background radiation, and large-scale structures. These methods come together to offer a detailed and evolving view of how space has been expanding since the Big Bang, enhancing our understanding of the universe's dynamic nature. Lastly, the future of the universe is a profound question in cosmology, with several theories proposing different endings based on our current knowledge of cosmological parameters, especially concerning dark energy, dark matter, and the universe's geometry and expansion rate. One main theory is the Big Freeze, or heat death. This scenario leans heavily on the idea of dark energy, which seems to be driving the universe's accelerated expansion. If this acceleration continues indefinitely, galaxies will drift further apart, leading to fewer interactions like galaxy mergers and star formations. Over billions and trillions of years, stars will use up their nuclear fuel, and the birth of new stars will come to a stop, leaving behind a universe filled with cold, dark leftovers like white dwarfs, neutron stars, and black holes. Eventually, even black holes might disappear through a method called Hawking radiation. As a result, the universe would end as a vast, chilly expanse filled with low-energy photons and basic particles. There's also the Big Crunch theory. In this version, the universe's expansion will stop and reverse if gravity's pull on the universe's matter, including dark matter, beats the push of dark energy. This reversal would make galaxies come together, increasing the universe's density and temperature. Finally, the universe might collapse back into a single point, similar to the Big Bang, possibly leading to a cycle of endless expansion and contraction. A theory related to the Big Crunch is the Big Bounce. In this idea, the universe goes through repeated cycles of growing and shrinking. After shrinking to a point like in a Big Crunch, quantum gravitational effects might trigger another explosion, starting a new growth cycle. This theory tries to combine quantum mechanics with general relativity to explain how the universe behaves when it's super dense. A more recently discussed possible end is the Big Rip. This idea comes from some dark energy models, particularly involving a type called phantom energy that gets stronger over time. If this dark energy grows more powerful than all other forces, it might eventually tear apart galaxies, stars, planets, and even atomic nuclei, leading to a universe where space itself comes apart. The Big Rip predicts a dramatic conclusion where the force driving expansion overwhelms every binding force on every level. Then there's the heat death scenario, distinct from the Big Freeze mostly in its focus on the universe reaching a state of thermodynamic equilibrium. Here, the universe hits maximum entropy, with all energy evenly spread out and no temperature differences to drive any kind of work. It would end up as a uniform, featureless space where the thermodynamic arrow of time essentially ends. Researchers keep refining these theories as our knowledge of dark energy, dark matter, and other cosmic elements grows. Observations, like those from the James Webb Space Telescope or gravitational wave detectors, will be key to narrowing down these models, shedding light on the universe's ultimate fate. Exploring and understanding dark matter and dark energy are some of the most thrilling and challenging tasks in current astronomy and physics. Both play crucial roles in the universe, yet they're hard to comprehend as they don't interact with light in observable ways. Scientists use various techniques to infer their existence and study their properties. Dark matter is detected through its gravitational effects on visible matter, radiation, and the universe's large-scale structure. Evidence includes the way galaxies rotate. Scientists find that outer stars spin faster than they'd expect if we only count visible mass, suggesting hidden mass, attributed to dark matter. Plus, the gravitational lensing, where light from distant objects bends around massive galaxy clusters, offers more proof. The bending is more than what visible matter alone would cause, indicating lots of dark matter. Efforts to directly detect dark matter are ongoing, using super-sensitive detectors deep underground to avoid cosmic rays and other noise. Experiments like the Cryogenic Dark Matter Search, CDMS, and the Xenon Dark Matter Experiment aim to catch the rare interactions between dark matter particles and regular matter. One path researchers are exploring involves accelerator experiments, like those at CERN's Large Hadron Collider, LHC, aiming to create and detect dark matter particles through high-energy collisions. Dark energy, however, is thought to push the universe to expand at an accelerating rate. We first got wind of it in the 1990s when Type Ia supernovae observations showed these distant stars were dimmer than anticipated, meaning the universe's expansion is speeding up. Although dark energy makes up about 70% of the universe, it's still quite the enigma. Scientists use different tactics to study dark energy, primarily observing large-scale cosmic structures like galaxy clusters and voids. Projects such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, chart these structures to track their evolution. The cosmic microwave background, CMB radiation, is another piece of this puzzle. Tools like the Planck satellite help us measure the CMB, revealing information about the universe's shape and expansion. Baryon acoustic oscillations, BAO, the pattern of sound waves from the early universe seen in galaxy distributions, also offer clues on how dark energy shapes the expansion rate. Future projects, like the Euclid satellite and the James Webb Space Telescope, JWST, promise to bring us groundbreaking data, while the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will conduct extensive sky surveys from the ground. Theoretical work is also ongoing to weave dark matter and dark energy into the fabric of particle physics and general relativity better. Exploring dark matter and dark energy uses a diverse strategy, mixing observations from telescopes, particle physics experiments, and theoretical advancements. Although they remain mysterious, studying them pushes our comprehension further, refining our understanding of what the universe is made of and what its future holds. Moving on to exoplanets, or planets outside our solar system, they present a rich variety in their size, makeup, and orbits, reflecting the vast diversity of planetary systems. Since the first confirmed discovery of exoplanets around the pulsar PSR B1257+12 in 1992, the field has rapidly grown, with thousands now identified thanks to cutting-edge detection methods and technologies. One of the key techniques for finding exoplanets is the transit method, where scientists watch a star's brightness over time. When a planet crosses in front of its star from our viewpoint, it causes the star's light to momentarily dim, a change known as a transit. By studying the depth, duration, and regularity of these transits, astronomers can gauge the planet's size, orbit, and even some atmospheric characteristics if the starlight passes through its atmosphere. NASA's Kepler Space Telescope majorly advanced this method, discovering over 2,000 exoplanets by watching a specific star field for faint brightness dips from planetary transits. Another well-known method is radial velocity, or the Doppler method, which observes how a star wobbles slightly due to the gravity of an orbiting planet. This wobble causes red and blue shifts in the star's light, detectable through the Doppler effect. By studying these shifts with high-accuracy spectrometers, researchers can determine the planet's mass and orbit, Telescopes equipped with devices like the HARP spectrograph in Chile have been critical in detecting exoplanets using this technique. Gravitational microlensing offers another fascinating way to find planets. It uses the gravitational pull of a large object, like a star, to bend light from a background star. If a planet is circling the nearest star, it can cause a noticeable temporary brightening in the background star's light, creating a microlensing event. This technique works really well for spotting planets that are far away from their stars, even in systems a few thousand light years out. However, it does need a perfect lineup and is often paired with other methods. Then there's direct imaging, which, while tricky, is becoming more popular. This involves snapping pictures of exoplanets by blocking the star's bright light, using tools like a coronagraph or a star shade. With the latest in tech and adaptive optics, capturing images of big exoplanets is possible, especially ones that are far from their stars. The James Webb Space Telescope is set to advance direct imaging, giving us the ability to examine exoplanet atmospheres closely. Astrometry comes in handy too. It's about tracking the precise movements of stars due to the gravitational pull of a planet. Although it's not used as often because it requires super accurate measurements, it's great for finding planets with long orbits. Whether these tools stand alone or work together, they help scientists figure out exoplanet masses, sizes, orbits, and atmospheres. Each new planet discovered reveals more about how planets form and whether they might support life, inching us closer to answering if life exists elsewhere. With missions like TESS, the James Webb Space Telescope, and future projects like ESA's Plato, the hunt and study of exoplanets remain an exciting field in modern astronomy. Scientists utilize several advanced methods to detect exoplanets, each with its perks and challenges. These techniques take advantage of the impact planets have on their stars and the light those stars emit. One of the most successful methods is the transit method, which involves watching a star's light for periodic dips in brightness. These dips happen when a planet crosses in front of the star, temporarily dimming its light. This transit can tell us about the planet's size and orbital period. NASA's Kepler Space Telescope has found over 2,000 confirmed exoplanets like this. By checking how the starlight changes during transit as it passes through the planet's atmosphere, scientists can figure out what gases are in the atmosphere, such as hydrogen, helium, and water vapor. Another key technique is the radial velocity or Doppler method. When a planet pulls on a star as it orbits, the star moves slightly, altering the star's spectral lines due to the Doppler effect. The star's light shifts to blue as it nears Earth and to red as it moves away. High-precision spectrometers, like those used in the HARP's instrument in Chile, can spot these slight shifts. This tells us about the planet's minimum mass and orbital eccentricity. Gravitational microlensing is a fascinating technique using a star's gravitational field to amplify the light from a farther background star when aligned closely. If this star has a planet, it can create an extra noticeable variation, known as a microlensing event. This method excels at finding planets far from their stars, including those several thousand light years away that other approaches might miss. Direct imaging aims to capture images of planets by blocking out their star's light, usually with a coronagraph or star shade to cut down glare. Although tough because planets are much dimmer than stars, advances in adaptive optics and space telescope technology make it more feasible. Direct imaging lets scientists study exoplanet atmospheres and even weather by looking at emitted or reflected light. Lastly, astrometry is all about tracking a star's exact position changes caused by a planet's gravitational pull. This technique demands super high accuracy since the shifts in position are really tiny. Although not used as frequently because of its tech demands, it's pretty good at spotting gigantic planets that orbit at a distance. These methods usually work great together, like if something's discovered using transit or radial velocity techniques, it can be checked out with direct visuals or looked into atmospherically during transits for a fuller picture. Each approach gets us closer to grasping the wide range of planetary systems in the galaxy and the chances for life beyond our solar hood. With tools like TESS, the Transiting Exoplanet Survey Satellite, JWST, James Webb Space Telescope, and ESA's PLATO, Planetary Transits and Oscillations of Stars, the search and study of exoplanets keep getting sharper and more enlightening, pushing the boundaries in finding alien life. Whether an exoplanet can support life hinges on a few crucial things, mainly if it can have liquid water, considered crucial for life as we know it. The major things to look at include the planet's spot in its star's habitable zone, its size and what it's made of, the atmosphere, and how steady and active its star is. This habitable zone, often called the Goldilocks zone, is the sweet spot around a star where it's not too hot or cold for liquid water to be on a planet's surface. This spot's distance shifts based on the star's kind and brightness. Say it's around a star like ours, the habitable zone could stretch from about 0.95 to 1.37 AU, with 1 AU being how far Earth is from the Sun. For a smaller, cooler type, like an M dwarf, the zone would be much closer. Finding a planet here is a major move towards checking if it can support life. The size and what the planet's made of also really matter. Ideally, a potentially life-friendly exoplanet should be Earth-sized or have a radius and mass not too far off from Earth, hinting it's more likely to be rocky and not a gas giant. Bigger planets might pull in thick hydrogen-helium atmospheres, making them more similar to Neptune or Jupiter, not Earth. Meanwhile, much smaller ones might not hold on to an atmosphere well, which is key for liquid water and shielding life forms from nasty stellar rays. The atmosphere of a planet is a big deal in balancing the temperature with the greenhouse effect, spreading heat, and providing necessary gases for possible life activities. A planet with enough air to keep heat in, but not so thick to get crazy hot like Venus, is thought to be more livable. Water vapor, carbon dioxide, and whiffs of gases like methane and oxygen are good signs. High-tech telescopes and spectrometers can peek into an exoplanet's atmospheric makeup during transits or by getting direct images, giving clues about life possibilities. The steady and active status of the home star matters a ton. Stars that get wild, like throwing intense solar flares all the time, might strip away atmospheres or soak planets in harmful rays, making life tough. So, stars with pretty steady outputs and long lives, like our Sun, are better for habitability. It's interesting that M dwarfs or red dwarfs, though cooler and dimmer, have mega-long lifetimes and have close-in habitable zones, but they might flare up a bit, which could threaten habitability. Other things to think about are the planet's tilt and how oval its orbit is, which both shake up seasonal changes and climate stability, plus the presence of a magnetic field that can protect the atmosphere from stellar winds and space radiation. Recent missions have spotted some exciting possibilities, like Proxima Centauri b, which orbits in the habitable zone of the nearest star to the Sun, and the TRAPPIST-1 system, home to several Earth-sized planets in its habitable zone. Future missions and telescopes, like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are set to give us a sharper look at distant worlds, analyzing their atmospheres and hunting for signs of life. Finding potentially habitable planets is a complicated process, with many factors playing a role in making a planet suitable for life as we know it, pushing forward our quest to discover another Earth among the stars. Imagine looking up into the skies of faraway planets, hundreds of light years away, as if you had a giant cosmic magnifying glass. That's exactly what astronomers do when they study the atmospheres of exoplanets, the planets circling stars outside our own solar system. One main technique they use is transit spectroscopy. When an exoplanet moves in front of its star, some starlight passes through the planet's atmosphere. By catching this light with powerful telescopes, scientists can study it to find out what molecules are present. Tiny features in the light spectrum, called absorption lines, give away the chemical makeup of the atmosphere. These clues can point to molecules like water vapor, carbon dioxide, methane, or other unusual substances, creating a vivid picture of these strange and faraway places. But figuring out what's in these alien atmospheres doesn't end there. Another important method, though much tougher, is direct imaging. When astronomers snag a direct image of an exoplanet, they can sometimes study the light bouncing off of it to learn about its atmosphere. Tools like the James Webb Space Telescope and other high-tech observatories use adaptive optics and coronagraphs to block out the bright light from the parent star, letting the dimmer light from the exoplanet shine through. By examining this light, scientists can figure out things like temperature, weather, and even if the planet might support life. This sophisticated approach, combined with theoretical models, helps scientists not only understand the atmospheric composition, but also guess the climate and conditions, unveiling whether these distant worlds could support life as we know it, or hold environments we can only dream about. In the vast cosmic sea where billions of stars rule, some exoplanets have grabbed the attention of scientists looking for life beyond Earth. One top contender is Proxima Centauri b, an Earth-sized planet orbiting in the habitable zone of Proxima Centauri, our nearest stellar neighbor at just 4.24 light-years away. Found in 2016, its position suggests liquid water might exist on its surface, a key ingredient for life as we know it. Continuous observations are working to uncover details about its atmosphere, surface, and potential for life, making it an exciting option in the search for alien neighbors. Meanwhile, the TRAPPIST-1 system presents another intriguing set of planets, with 7 Earth-sized ones orbiting a cool dwarf star just 39 light-years away. Interestingly, 3 of these planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are in the star's habitable zone. These planets have such tight orbits that a year on one might last only a few days by Earth standards. Spectroscopic studies of the TRAPPIST-1 worlds are already shedding light on their atmospheres. Their size, density, and distance from their star hint they might have liquid water and maybe even life. The TRAPPIST-1 system acts as a perfect lab for examining exoplanet atmospheres and assessing the potential for life beyond our planet, making it a key focus in the hunt for the extraordinary within our galaxy's everyday vastness. The Drake equation is a fascinating intellectual tool created to estimate how many active, communicative, extraterrestrial civilizations might be in the Milky Way. Developed by astrophysicist Frank Drake in 1961, the equation provides a way to break down a seemingly impossible task into manageable parts, making the complex search for extraterrestrial intelligence a bit more understandable. These elements cover the rate at which stars form in a galaxy, how many of those stars have planets, and how many planets might support life in each solar system. Moving forward, it considers the chance of life emerging, the odds of intelligent life developing, and whether such intelligent beings create technology to communicate over interstellar distances. Each part of the Drake equation relies on observational data, theoretical know-how, and a bit of educated guessing, as some aspects are still largely uncertain. While we have lots of data on star formation and exoplanet prevalence, thanks to missions like Kepler, the emergence of life, the rise of intelligence, and the longevity of technological civilizations are less certain. Despite these uncertainties, the true strength of the Drake equation lies in its structure, helping scientists methodically search for extraterrestrial intelligence, or SETI. Updating the equation with new data helps scientists refine their estimate of how many civilizations might be out there, pondering the profound question, are we alone in the galaxy? With international cooperation and technological progress, the quest inspired by the Drake equation continues, always adapting to the expanding frontiers of astronomical knowledge. The Apollo missions are unforgettable landmarks in human achievement, with Apollo 11 landing on the moon in 1969 being a timeless memory for humanity. This incredible moment saw Neil Armstrong and Buzz Aldrin become the first humans to step on another world, a testament to the boundless ingenuity and determination of those involved. Armstrong's famous words, "That's one small step for man, one giant leap for mankind," captured the importance of this groundbreaking mission. The Apollo program wasn't just about planting a flag and leaving footprints. It also returned with over 840 pounds of lunar rocks, soil, and core samples, fundamentally changing our understanding of the moon's makeup and history. Yet, the Apollo missions were about more than reaching the moon and coming back. They showcased scientific exploration and technological advancement at its finest. The missions led to major advances in many fields, from computing to engineering. The Saturn V rocket, the most powerful ever built, safely sent astronauts beyond Earth's gravity. Scientific tools left on the moon, like seismometers and retroreflectors, offered valuable data on the moon's internal structure and its interaction with Earth. Apollo 12 through Apollo 17 expanded this achievement with extended explorations, scientific instruments deployment, and lunar roving vehicles that allowed astronauts to wander farther. These Apollo successes laid the foundation for today's space exploration, inspiring what's possible when human ambition and scientific inquiry come together. The International Space Station, ISS, stands as a top example of international teamwork and scientific exploration, flying about 250 miles above Earth. Since it began in 1998, the ISS has been crucial for experiments not possible on Earth due to gravity. Long missions have allowed scientists to study microgravity's effects on the human body, giving essential insights for future astronauts who might travel to Mars and beyond. Research on muscle loss, bone density decreases, and fluid shifts in the body has led to countermeasures and a better grasp of space travel's impact on human health, key for long-term space survival. Beyond biology, the ISS serves as a lab for many scientific fields. Physics studies, for example, benefit from microgravity to explore fluid dynamics and combustion in ways not possible on Earth. The ISS has become a hub for studying space and Earth from above. With instruments on board, researchers have checked out cosmic rays, searched for dark matter, and closely watched Earth's atmosphere, oceans, and land, playing a big part in monitoring climate change and natural disasters. Plus, the international teamwork on the ISS has not only boosted technology, but also brought countries together, showcasing how space exploration can unite people. Using its unique spot in low Earth orbit, the ISS continues to be a symbol of scientific growth and a key part of future deep space missions. The Mars rovers Curiosity and Perseverance are leading the charge in uncovering the secrets of Mars. Sent by NASA, these cutting-edge robotic explorers are there to dig into Mars' past and check if it ever had conditions that could support life. Curiosity, since landing in Gale Crater in 2012, has been on a mission to find out whether Mars might have once had the right environment for tiny life forms. Loaded with scientific gear, Curiosity has analyzed rocks and soil for traces of organic material and other signs of a habitable past. Finding ancient riverbeds and lake beds, along with complex organic molecules, the rover has already delivered convincing clues that Mars might have been friendly to life eons ago. Perseverance, landing in Jezero Crater in 2021, continues the mission, but goes even further in the hunt for signs of past life. Its main goal includes gathering and storing soil and rock samples, possibly containing signatures of ancient life, all to be brought back to Earth later for detailed study. Perseverance also boasts new tech for examining Mars' geology and climate, and even looks for future human landing spots. It also brought Ingenuity, a small helicopter, proving powered flight on another world is doable, paving the way for future aerial missions. Together, these rovers are setting the stage for more findings and paving the way for human Mars exploration, shifting our understanding of the planet with every new discovery. Voyager and New Horizons are standout examples of human innovation, each setting off on awe-inspiring missions to see the far ends of our solar system and beyond. Launched in 1977, the twin Voyager spacecraft were initially all about exploring the outer planets. Voyager 1 and 2 provided never-before-seen images and data from Jupiter, Saturn, Uranus, and Neptune, greatly expanding our knowledge of these far-off places. Outfitted with cameras, magnetometers, and plasma detectors, they uncovered the details of Jupiter's rings, Saturn's and Neptune's unique atmospheres, and the volcanic activity on Io, a moon of Jupiter. But they didn't stop there. Both Voyagers eventually cruised into interstellar space, becoming the first man-made objects to leave the heliosphere, bringing back crucial info about the vast space beyond our sun's reach and broadening our understanding of our galactic neighborhood. New Horizons, which took off in 2006, showcased a focused mission to investigate Pluto and the Kuiper Belt. After nearly 10 years on the road, it reached Pluto in 2015, sending back detailed pictures and data that reshaped our view of this distant dwarf planet. The mission unveiled Pluto's fascinating features, such as tall mountains and large nitrogen ice plains, challenging previous ideas of what such a far-off world might look like. After its Pluto success, New Horizons targeted another goal, a Kuiper Belt object called Arrokoth, finally reaching it in 2019. The flyby gave us a peek into the basic building blocks of our solar system, showing us a primitive world with a surprisingly smooth and almost flawless surface. The missions from Voyager and New Horizons highlight our never-ending curiosity and desire to learn more. They didn't just supply a wealth of scientific info, but also shone as guides to the endless possibilities waiting for us in space. Each milestone pushes what's possible in space exploration. Now, as we aim to go back to the Moon and head to Mars, the goals of these upcoming missions are both bold and varied, covering scientific research, new tech, and laying the groundwork for potential human settlements. NASA's Artemis program plans to have the first woman and the next man land on the Moon by the mid-2020s. A major goal is setting up a long-lasting human presence there by the decade's end. This will include building the Lunar Gateway, a space station orbiting the Moon that will be a hub for future missions. By studying the Moon's surface and resources, such as any water ice in shadowed craters, scientists hope to figure out how these can support life and fuel, making living on the Moon more doable. Scientifically, lunar missions will delve into the Moon's geology, origins, and history. By examining its surface and core samples more closely, scientists hope to uncover secrets about the early solar system and Earth's formation. The Moon is also a great place to test technology and life support systems for farther missions, making it an essential step towards Mars exploration. Mars presents even more exciting goals as it poses scientific and existential questions about our place in the universe. Future missions, led by NASA, ESA, and companies like SpaceX, aim for human exploration of Mars. They will build on the work of robots like Curiosity and Perseverance, focusing on colonization prospects, developing habitats to withstand Martian conditions, mastering resource use on Mars, like extracting water and making oxygen, and creating sustainable energy. Scientifically, Mars missions aim to look for past or present life, study its climate and geology, and understand its atmospheric and surface changes. This involves drilling into Mars's surface and even bringing samples back to Earth for detailed study. These efforts don't just aim to answer big questions about Mars, but also prep us for living on another planet, which could be key to ensuring our future. Each advance on these celestial bodies is a huge step toward becoming a multi-planet species, driven by exploration and the quest for knowledge. Space telescopes like the Hubble and the James Webb have changed how we understand the universe, giving views and insights that ground-based observatories can't. Since launching in 1990, Hubble has looked deep into space with its sensitive tools, capturing amazing images of galaxies, nebulae, and distant stars. Hubble's discoveries, like the universe's accelerated expansion, confirmed through its supernova studies and distant galaxy redshifts, suggest dark energy is driving this expansion. Its high-res images have refined our understanding of star life cycles and galaxy formation and evolution. By capturing detailed images of the early universe, Hubble has let astronomers study the first stars and galaxies, giving insights into conditions right after the Big Bang. The ability to see in ultraviolet, visible, and near-infrared wavelengths lets scientists explore different cosmic events over a wide range, making it a highly useful tool for all sorts of astronomical studies. The James Webb Space Telescope, which took off in December 2021, promises to expand these capabilities even more. It mainly works in the infrared spectrum, giving it the power to look through thick cosmic dust clouds that block visible light, offering never-before-seen glimpses of the universe's earliest structures. One major mission for JWST is to look at the first light-producing objects that appeared in the universe, studying how the earliest galaxies formed and evolved. Its sophisticated instruments will enable a detailed look at the atmospheres of exoplanets in search of signs that might suggest they can support life, or even biosignatures that hint at the possibility of life. Furthermore, JWST will deliver unmatched insight into how stars and planets form, closely investigating the molecular clouds where new stars and planetary systems germinate. By capturing very detailed spectra, JWST will be able to probe the chemical makeup of these areas, helping us learn more about how the building blocks of planets and possibly life itself come about. Together, Hubble and JWST are a powerhouse pair of space telescopes, each bringing unique abilities to the table that complement one another, greatly broadening our understanding of the universe and putting us on the edge of new astronomical breakthroughs. Dark matter, a mysterious and unseen piece of the universe's puzzle, plays a critical role in the vast cosmic framework. Even though it doesn't emit, absorb, or reflect light, making it invisible to telescopes, its existence is detected through its gravitational effects on visible matter and the large-scale setup of the universe. Dark matter makes up about 27% of the universe's total mass energy, far outweighing the regular baryonic matter that forms stars, planets, and galaxies, which is only around 5%. The other 68% is made up by dark energy, a puzzling force that's driving the universe to expand faster and faster. The importance of dark matter first came to light in the 1930s, when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving much faster than they should be, based on the visible mass of the cluster. Then, in the 1970s, Vera Rubin's research on spiral galaxies' rotation curves provided more convincing proof. The outer parts of galaxies were spinning at rates that couldn't be explained by the visible stars and gas alone, suggesting there was a hefty amount of unseen mass or dark matter providing the gravitational force needed. In cosmology, dark matter is vital for a few reasons. First off, it acts as the framework for structure formation in the universe. Back in the early universe days, dark matter clumped together under gravity's pull, creating the cosmic web pattern that serves as a foundation for galaxy formation. Without dark matter, galaxies, clusters, and superclusters wouldn't have formed the way we see them now. Second, dark matter helps us make sense of gravitational lensing, where a massive object's gravitational field, like that of a galaxy cluster, bends the light from things behind it. This bend in light uncovers dark matter regions, helping us map out its distribution across the universe. Lastly, getting a grip on dark matter is crucial for a full theory of fundamental physics. Although various potential candidates like weakly interacting massive particles, WIMPs, and axions have been suggested, the final discovery and identification of dark matter particles are still out of reach. Figuring out what dark matter is could bridge gaps in the standard model of particle physics and provide insights into some of the universe's deepest secrets. Dark matter stands as a cornerstone in our quest to understand the cosmos, weaving together the worlds of cosmology, astrophysics, and particle physics. Dark energy, that baffling force causing the universe to speed up in its expansion, remains one of the biggest mysteries in today's cosmology. First guessed at from distant supernovae observations in the late 1990s, dark energy makes up about 68% of the universe's total mass energy content. Dark energy works in a way opposite to gravity, unlike dark matter, which pulls things together. So instead of slowing down, the universe is speeding up its expansion. Researchers dig into dark energy mainly by looking at the universe through telescopes, and they use a few main tricks. One major approach involves type Ia supernovae, those big explosions with reliable brightness, which makes them perfect for measuring distances in space. By checking how bright these supernovae appear and comparing it to how much their light has shifted, scientists realized galaxies are zooming away faster than expected. This unexpected result hinted at a mysterious force, knocking gravity out of its usual role, now tagged as dark energy. Another cool method is looking at the cosmic microwave background, CMB radiation, the lingering glow from the Big Bang. Space missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have gathered tons of details about the early universe and its growth over time. These CMB variations give clues about the universe's shape, makeup, and expansion journey, underlining dark energy's influence on cosmic development. Surveys covering large sections of the universe also help in unraveling dark energy's mysteries. Big projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, chart the galaxy spread across vast universe parts, allowing scientists to track how cosmic structures changed over time. Baryon, acoustic oscillations, BAOs, are another handy measure, acting like a cosmic yardstick to gauge changes and expansions in the universe story. By observing these BAOs, researchers get a peek into how dark energy messes with the universe's expanding routine across different times. On the ideas front, theories about dark energy churn up loads of chit-chat in physics circles. Some folks think dark energy is tied to space itself, as suggested by the cosmological constant in Einstein's general relativity equations. Others imagine it's a changing field called quintessence, shifting over the ages. There are also wilder theories adjusting gravity's work on a cosmic scale. By blending these insights from observations and theory, scientists piece together a rich tapestry about dark energy, even though it remains something of an enigma. As teams readies future missions like the Euclid Telescope and the Wide Field Infrared Survey Telescope, WFIRST, there's great hope for more clues on this cosmic brain teaser, inching closer to fully grasping the universe's forces. Gravitational waves, ripples in space-time, pop up during the universe's most intense events. Albert Einstein first predicted them in 1916 as part of his groundbreaking general relativity theory. When massive things like binary neutron stars or black holes stir things up, they ripple through space-time, spreading out at light speed and carrying energy with them. Fast forward nearly a century to September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, caught these waves directly for the first time. It was a game changer in astronomy, confirming gravitational waves exist and offering a fresh way to explore the universe apart from regular light. LIGO uses a smart tool called laser interferometry for this. It has two setups located in Livingston, Louisiana and Hanford, Washington, each with two 4-kilometer-long arms shaped like an L. A powerful laser beam splits, moving down these arms and bouncing off mirrors, creating an interference pattern. When a gravitational wave sweeps through Earth, it makes space wiggle, creating tiny shifts in the distance between mirrors. These minuscule changes, about the size of a fraction of a proton's diameter, affect the interference pattern, indicating a gravitational wave's presence. The very first event detected, known as GW150914, came from two black holes crashing together roughly 1.3 billion light-years away. The black holes, with masses 29 and 36 times that of our Sun, spiraled in until they formed a bigger black hole. This explosive event unleashed an incredible energy burst as gravitational waves, confirming binary black hole systems exist and showing they can merge. This groundbreaking discovery opened up a whole new view into the universe, helping scientists explore phenomena we couldn't see before. Since then, gravitational wave astronomy has grown, catching more events like neutron star mergers. One such event, GW170817, was seen in both gravitational and electromagnetic waves, kicking off a new era in multi-messenger astronomy. With ongoing improvements like LIGO upgrades and new detectors like Virgo in Italy and Kagura in Japan, we're on the path to better understanding the universe, potentially revealing unknown astrophysical processes and offering insights into how gravity works at its core. Fast radio bursts, or FRBs, and other mysterious space signals are some of the most baffling puzzles modern astrophysics faces. These bursts are super quick yet powerful spikes of radio waves, lasting just a few milliseconds, but each can pack as much energy as the Sun emits in a day. The first FRB was discovered in 2007, and since then, many have been found, each piling on more questions about where they come from and how they work. One big challenge with FRBs is figuring out where exactly they originate. Some FRBs appear once, while others, like FRB 121102, pop up repeatedly. This difference hints that there might be various sources or ways these bursts happen. The discovery of repeating FRBs led to big breakthroughs, like locating a particular repeating source in a star-forming region of a small galaxy about 3 billion light-years away. This find gives clues but leaves many theories on the table, from highly magnetized neutron stars and magnetars to collapsing black holes, or even wild theories involving extraterrestrial life using powerful energy sources. Another puzzling signal testing our understanding of space is the WOW signal, caught in 1977 by the Big Ear radio telescope. This strong, non-repeating narrowband radio signal had features suggesting an artificial origin, sparking talk about intelligent alien communication. Despite numerous follow-ups, no similar signals have been found, keeping its source a fascinating mystery. These puzzling signals push the limits of our current astrophysical theories and what we can observe. Studying FRBs could also boost our understanding of the intergalactic medium. As these radio waves travel through space, they interact with electrons, causing delays in arrival times for different frequencies. Analyzing this dispersion helps scientists learn about the density and spread of intergalactic matter, offering a new way to explore the cosmos on a large scale. Moreover, studying these mysterious signals drives the need for more advanced detection techniques and equipment. Radio telescopes like CHIME in Canada and ASCAP in Australia are at the forefront of scanning the skies for these hard-to-catch bursts, boosting the detection rate and creating a detailed FRB catalog. These advancements push technological development in radio astronomy and data analysis techniques. To sum it up, FRBs and other cosmic signals aren't just mind-blowing phenomena. They're also driving forces for scientific and tech innovation. They broaden how we see the universe and might just reveal new sides of the fundamental rules that run everything. Delving into these puzzling signals is a major area in astrophysics, with future discoveries that could totally change how we understand the cosmos. The idea of parallel universes and the multiverse stands out as one of the most exciting and speculative theories in today's cosmology and physics, hinting that ours might just be one among countless other unique universes. A few top theories back up the existence of these parallel worlds, each built on different facets of physics and cosmology. One key theory is the many worlds interpretation, or MWI, from quantum mechanics, which physicist Hugh Everett introduced in 1957. MWI suggests that each quantum event with multiple outcomes results in the universe branching out, each branch representing a different outcome. For example, if a particle has a 50-50 chance of being in one of two states, the universe divides into two, with each branch showcasing one of the states. This could mean that every possible outcome unfolds somewhere, leading to a vast, maybe limitless number of parallel universes where every conceivable timeline exists. Another intriguing idea comes from inflationary cosmology, notably the theory of eternal inflation from physicist Alan Guth and others. This theory argues that the universe's rapid expansion right after the Big Bang wasn't uniform. While some areas stopped expanding and formed distinct universes like ours, others kept going. This process creates a multiverse of bubble universes, each potentially having different physical properties and constants. These bubble universes might never interact with one another, making detection incredibly tough, but implying a vast range of parallel realities within an ever-expanding space. Then there's string theory, a foundational concept in theoretical physics, which introduces the idea of a landscape multiverse. It suggests that our universe might be just one of a myriad of string configurations, each tied to a distinct vacuum state and fundamental constants. This range of configurations makes up a landscape where numerous universes exist, each with its own physical laws. Within the string theory landscape, universes could vary in dimensions, particle types, and interactions, forming a rich and varied multiverse. Further along is the brane multiverse concept, stemming from certain interpretations of string theory and M theory. Here, our universe is seen as a three-dimensional brane floating in a higher dimensional space, with other branes representing different universes potentially existing parallel to ours. Sometimes these branes might interact or even collide, possibly explaining cosmic events like the Big Bang in our universe. Such theories about parallel universes and the multiverse, despite being largely speculative, open up fascinating possibilities about reality, suggesting our universe may be just a small piece of a far more complex cosmic puzzle. Both scientists and philosophers wrestle with the deep meanings behind these ideas, contemplating questions about existence, reality, and the universe's ultimate nature. Though we haven't nailed down hard evidence for parallel universes yet, progress in theoretical models and observational tools might eventually give us clearer clues about these captivating realms. Investigating cosmic phenomena like quasars and blazars involves a mix of cross-wavelength observations, advanced theoretical models, and cutting-edge computational tools. These mysterious objects, powered by supermassive black holes at galaxy centers, shine a light on some of the most energetic processes in the universe. Quasars, short for quasi-stellar objects, are incredibly luminous. Back in the 1960s, scientists first recognized quasars because they emitted strong radio waves. Later on, they realized these cosmic objects also gave off energy across the entire electromagnetic spectrum, including visible light, ultraviolet rays, infrared, X-rays, and even gamma rays. Quasars glow so brightly because they feed off material falling into the supermassive black hole at their centers. As this stuff swirls toward the black hole, it forms an accretion disk where gravity is turned into light and other forms of radiation. Sometimes, quasars shine brighter than their entire host galaxies, making them visible over incredible distances in space, which makes them important for studying the universe's early days. Blazars are a special type of quasar where the jets are aimed almost right at Earth. This orientation causes something called relativistic beaming, which focuses the light and makes blazars appear super bright and variable. Blazars are split into groups like BL Lacertae objects, BL Lax, and flat-spectrum radio quasars, FSRQs, depending on how they emit energy. Studying blazars helps scientists understand the mechanics behind jet formation, particle acceleration, and how these jets interact with the space around them. Astronomers use various tools to check out these cosmic wonders, covering all parts of the electromagnetic spectrum. For example, radio telescopes, like those at the Very Large Array, VLA, or the Atacama Large Millimeter-Submillimeter Array, ALMA, observe the radio waves from quasars and blazars, revealing jet structures and dynamics. Optical and ultraviolet observations from ground-based perspectives and space-based telescopes, like the Hubble Space Telescope, focus on light from the accretion disk and its surroundings. X-ray telescopes, such as Chandra, and gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope, delve into high-energy emissions to give clues about how particles accelerate and energy dissipates in jets. Spectroscopy is important for breaking down the data. By studying the spectra of quasars and blazars, scientists can figure out their redshift, indicating their distance and how fast the universe was expanding at different times. Spectroscopy also reveals details like the chemical makeup, speed, temperature, and density of the stuff emitting and absorbing light, which helps model what's happening around the supermassive black hole. Theoretical models and computer simulations work alongside observations to give a clearer picture of how quasars and blazars behave. These models simulate accretion disks, magnetic fields, jet formation, and the radiation processes, offering insight into the physics involved. By combining observation and theory, scientists can start to decode the complex systems powering these phenomena, shedding light on galaxy life cycles, black hole growth, and the overall evolution of the universe. Studying quasars and blazars gives scientists a broader understanding not only of these brilliant celestial lights, but also of the basic processes that shape the cosmos. This ranges from how structures formed early on in the universe to the energetic feedback mechanisms that affect galaxy development. On a different note, astrobiology is the science investigating life beyond Earth, blending fields like biology, chemistry, physics, and astronomy. Researchers in this area aim to uncover how life begins, changes, and where it might exist in the universe. They tackle intriguing questions. Are we the only ones here, or is life elsewhere too? How do living things adapt to extreme conditions? To find answers, astrobiologists examine both earthly and alien environments, searching for places where life might exist. Within our solar system, they look at Mars' surface chemistry, the icy moons of Jupiter, like Europa, and Saturn's moon Enceladus, which has oceans underneath that could host microbial life. Spectroscopy and other advanced techniques help detect potential biomarkers in the atmospheres of exoplanets, planets circling stars outside our solar system. These studies rely on data from New Age telescopes, rovers, and space probes. In labs, scientists recreate space-like conditions to understand how life might endure harsh environments, from the emptiness of space to the harsh radiation on Mars. By examining Earth's extremophiles, organisms that thrive in hot springs, deep-sea vents, and radioactive waste, researchers uncover crucial hints about life's toughness and adaptability, setting the stage for future cosmic discoveries. Extremophiles are unique microorganisms that live in environments too harsh for most life, adapting to extreme temperatures, acidity, saltiness, and radiation. The study of these organisms broadens our view of possible life beyond Earth and helps scientists pinpoint where and how to look for alien life. For instance, bacteria that withstand the intense heat of ocean floor hydrothermal vents, or those that survive in radioactive or highly acidic areas, show the incredible resilience of life. This knowledge directs scientists to investigate similar extreme places across our solar system and beyond. For example, extremophiles that love acidic environments and thrive in sulfuric hot springs give clues about Mars. There, sulfur compounds are abundant, hinting that if life ever existed on Mars, it might mirror these tough Earth bacteria. Moreover, discovering extremophiles surviving in ice or below permafrost suggests potential life on the icy moons of Jupiter and Saturn, like Europa and Enceladus. These moons have subsurface oceans warmed by tidal forces, offering habitats where extremophiles might flourish. Additionally, researchers use extremophiles to develop methods to spot biosignatures, chemical life signs, in exoplanet atmospheres. By understanding the metabolic and chemical workings of extremophiles, scientists refine their tools for detecting life in the universe's strangest places, helping guide future missions. Mars is one of the solar system's top spots for finding microbial life. Its history with liquid water, crucial for life, has long fascinated scientists. Recent seasonal methane plumes and dark surface streaks hint that liquid water might still flow on Mars at times. Methane is compelling because it might come from life, though geological processes can also create it. The discovery of complex organic molecules in Gale Crater by the Curiosity rover strengthens the idea that Mars might have hosted microbial life in the past and perhaps still does in underground refugees. Jupiter and Saturn's icy moons, particularly Europa and Enceladus, are also prime candidates for harboring microbial life. Europa's thick ice conceals a global watery ocean warmed by Jupiter's tidal forces. Observations from the Galileo spacecraft and Hubble Space Telescope suggest water vapor plumes might burst from Europa's surface, pointing to an active ocean beneath that could support life. Enceladus, Saturn's moon, drew interest due to its dramatic geysers shooting water vapor, organic molecules, and salts into space from its southern pole. These plumes, coupled with proof of seafloor hydrothermal activity in Enceladus's subsurface ocean, make it a top candidate for life. Such places offer not just water, but also energy and life's chemical building blocks, making them crucial for future missions. Missions like exploring Mars are vital to astrobiology, directly investigating places that might once have been or may still be habitable. The rovers and orbiters sent to Mars are equipped with advanced tools to examine the planet's geology, climate, and potential biosignatures. For example, NASA's Perseverance rover, which landed in 2021, is closely analyzing Jezero Crater. A spot that might have been a river delta and lake in the past is being explored. Perseverance is checking out sedimentary rocks that can keep and guard organic molecules, hoping to find hints of ancient microbial life. These space missions give us crucial info on how water used to flow, what organic chemistry looked like, and all the conditions that could have supported life. What Mars missions teach us plays a big role in astrobiology. For example, the SAM tool on the Curiosity rover can find various organic compounds and check isotopic ratios, giving us a glimpse into Mars' old environments and whether life was possible there. Techniques like these are essential for figuring out if biosignatures exist, not just on Mars, but other places too. Plus, what we learn helps us develop new tools for future missions, like Europa Clipper, which will explore Europa's habitability, and the Dragonfly mission to Titan. Each mission helps refine our search for life and makes clear just how interlinked astrobiological studies are. Spotting life beyond Earth would have huge impacts on our grasp of biology, the beginnings of life, and our part in the cosmos. Finding alien life, even in the tiniest forms, would shake up our view of life's uniqueness and how adaptable it is. If there's life elsewhere, it'd imply that life can start in various conditions, suggesting it might be more widespread in the universe than we ever believed. Such a find would make scientists rethink the assumed necessary conditions for life and widen the places they investigate. On another level, finding extraterrestrial life would have massive philosophical, cultural, and possibly even religious effects. It'd question long-held beliefs about our central spot in the universe, maybe changing how humanity sees itself and its role. What if we're not alone? Debates would kick off about our connection with the cosmos and our duty to take care of Earth. Moreover, the quest for alien life could spark a burst in science and tech, just like the space race did back in the day. Boosting tech for space missions might lead to breakthroughs helping Earth, like new materials and better communication and data tech. Discovering life off-world would shake up what we know about biology and deeply affect our culture, tech, and worldview. To hunt for life signs on exoplanets, scientists use clever strategies, relying on advanced tech and deep insights into life's telltales. Central in this push are high-power space telescopes with tools that can analyze light from distant stars and their planets. By checking out the absorption lines in the spectrum, scientists can identify molecules like oxygen, methane, and water vapor that hint at biological activity. Upcoming projects like the European Space Agency's aerial plan to examine varied exoplanet atmospheres. Other methods involve directly imaging the planets, using tech to block out their bright host stars, so the planet's faint reflected light can be analyzed. This approach allows scientists to see surface details and atmospheric makeup, possibly spotting biosignatures like chlorophyll or photosynthesis-related pigments. Telescopes like the Extremely Large Telescope, ELT, being built in Chile, are set to pitch in with space-based efforts by offering high-resolution images and spectroscopy. These observatories will allow us to dive into the details of exoplanet atmospheres and terrains, searching for strange signs like unusual gas levels or unique colors hinting at life. By using these methods, scientists are systematically hunting for life's clues across the galaxy, trying to understand how life might show up in the diverse settings of distant planets. The idea of humans living on Mars is thrilling yet daunting, bringing both big challenges and new chances. With many space agencies and private companies eyeing Mars, it's seen as the most realistic spot for future colonies because it's relatively close to Earth and might have usable resources. Organizations like NASA and SpaceX are working hard on tech and plans to help humans live on Mars sustainably. NASA's Artemis program, which aims to send humans back to the Moon, is seen as a stepping stone to Mars, using lunar missions to test out important tech. Meanwhile, Elon Musk's SpaceX is pushing forward with the Starship, a spacecraft that aims to carry humans and cargo to Mars. A big part of making Mars livable is the idea of using local resources, or in situ resource utilization, ISRU, like turning Martian carbon dioxide-rich air into oxygen or using Martian soil for building shelters. But serious challenges remain, such as dealing with radiation, since Mars doesn't have a protective magnetic field or thick atmosphere like Earth does. Taking care of astronauts' mental and physical health during the long trip and once on Mars is another major issue. Plus, developing life support systems, communication networks, and ways to grow food sustainably are crucial for setting up human colonies on Mars. Experiments on Earth, such as closed-loop systems tested in places like the Hawaii High Seas habitat, aim to tackle these problems before humans actually set foot on Mars. Although the obstacles are big, recent progress feeds optimism. The vision of creating independent colonies on Mars is fueled by scientific curiosity, tech advances, and the human drive for exploring and surviving. Space agencies everywhere are carefully plotting how to overcome the many hurdles of long space journeys, which are key for missions to Mars and beyond. A top concern is keeping astronauts healthy during long spells in microgravity, as being weightless for too long can weaken muscles and bones. To fight these effects, agencies like NASA and ESA have crafted special exercise routines and equipment to keep astronauts in shape. Additionally, they're looking into artificial gravity, maybe by creating rotating parts of spacecraft, as a potential fix for the downsides of weightlessness. Dealing with radiation is also a big worry, since once outside Earth's protective magnetosphere, space travelers face increased exposure to cosmic rays and solar radiation. Spacecraft shields are constantly being improved with materials that better absorb or block harmful radiation. NASA is even looking into using water and polyethylene shields, along with creative ideas like magnetic fields to protect spacecraft. Progress in medical tech, including telemedicine and small medical kits that can manage various health issues, is vital too. These systems are needed to ensure astronauts get prompt medical help, even when far from Earth. Psychological resilience is just as crucial, since astronauts have to handle isolation, confinement, and the stress of lengthy missions. Agencies are tackling mental health with thorough pre-flight psychological prep, designing spacecraft with more comfortable interiors, and giving ongoing in-flight support, including virtual reality experiences that replicate aspects of life on Earth. Communication delays, which are unavoidable on long missions, are addressed through creating autonomous systems and artificial intelligence on spacecraft, allowing crews to operate independently if instant contact with mission control isn't possible. By combining tech innovations, intense training, and creative research, space agencies are crafting a broad strategy to handle the challenges of long space journeys, paving the way for humanity's exploration of the final frontier. Private companies like SpaceX are becoming increasingly important in the future of space exploration, shaking up the industry with their cutting-edge technologies, cost-saving solutions, and daring goals. In the past, space exploration was mainly led by government space agencies like NASA, Roscosmos, and ESA. But now, the involvement of private companies has kicked off a new age of commercial spaceflight, marked by quick advancements and lowered costs. SpaceX, for example, has made big progress with reusable rocket tech, which has significantly slashed the expenses of launching stuff into space. The Falcon 9 rocket, famous for returning to land after delivering its cargo, showcases this game changer, making missions more frequent and affordable. One of the standout contributions of SpaceX and other private firms is their part in supporting missions to the International Space Station, ISS, and beyond. SpaceX's Dragon spacecraft has been vital for transporting supplies and crews to the ISS through NASA's Commercial Crew Program. This partnership not only eases NASA's logistical load, but also lets the agency concentrate more resources on exploring deeper into space, like Mars and the Moon missions. Plus, SpaceX's bold Starship project aims to create a fully reusable ship to carry humans to Mars, aligning with long-term dreams of planetary settlement and interplanetary travel. Such ventures are stretching the limits of what's possible, speeding up the timeline for human journeys to other planets and moons. Moreover, the involvement of private enterprises encourages a competitive and cooperative space economy, spurring innovation across the board. With projects like SpaceX's Starlink for global satellite internet and Blue Origin's work on space tourism and lunar landers, the space exploration scene is quickly diversifying. These initiatives not only push tech capabilities forward, but also spark public interest and funding in space activities. Private companies are turning space exploration from a government-run operation into a lively, multi-directional industry, pushing progress through innovation, efficiency, and visionary projects that bring humanity closer to becoming an interplanetary species. Space tourism is set to take off rapidly in the next few decades, driven by tech progress, more private sector involvement, and growing public curiosity about experiencing space firsthand. The first steps in space tourism are already underway, with companies like SpaceX, Blue Origin, and Virgin Galactic taking the lead. Each of these companies has developed unique ways to make space more accessible. For instance, Virgin Galactic offers suborbital flights, letting participants experience a few minutes of weightlessness and stunning Earth views from the edge of space. Blue Origin's New Shepard rocket offers a similar trip with a fully automated system designed to carry tourists to the Kármán line, the boundary of space. Looking ahead, space tourism is expected to expand beyond short suborbital trips to include longer and more immersive experiences. In the coming decades, staying in orbit might become a reality, with private companies offering visits to orbiting space stations or habitats. These space hotels could let guests experience living and working in microgravity, try out scientific experiments, and soak in incredible views of Earth from orbit. Companies like Axiom Space are already working on commercial modules for the International Space Station, which might later turn into independent space habitats. On top of that, big ideas like SpaceX's Starship are thinking of taking tourists for trips around the moon, offering a truly mind-blowing adventure. As tech moves forward and it becomes cheaper to launch and keep people in space, space tourism might even reach the moon or Mars. Down the line, we might see the building of bases or colonies, giving travelers a shot at checking out otherworldly landscapes and being part of the early steps of settling in space. This will probably be backed by breakthroughs in life support systems, building habitats, and using resources from the environment, making sure these adventures are both safe and doable. In time, the expansion of space tourism will not only open up new frontiers for exploration and fun, but also spark tech advances and get more people around the world excited about space science, pushing humanity closer to the dream of living on multiple planets. Asteroid mining offers a tempting mix of potential benefits and big risks that need careful handling. On the plus side, asteroids are packed with valuable stuff like metals such as iron, nickel, and cobalt, plus precious ones like platinum and gold. These are key for many industries on Earth, especially in electronics and renewable energy tech. Mining these asteroids could ease the stress on Earth's resources and cut down the environmental damage from mining here. Plus, some asteroids have water that can be split into hydrogen and oxygen to fuel missions further into space, possibly making exploring the solar system more affordable and sustainable. Asteroid mining also promises to boost economic growth and tech innovation. The new mining techniques and space travel tech could spark advances that help other areas like robotics, AI, and materials science. If asteroid mining proves to make business sense, it could kickstart new markets and jobs, promoting a space-based economy that furthers the exploration and use of space resources. Securing a steady supply of needed raw materials could also strengthen national security and economic stability, cutting reliance on earthbound sources that might be geopolitically sensitive. But these potential upsides come with serious challenges. The technical and logistical hurdles of asteroid mining are daunting, from finding and reaching the right asteroids to developing effective ways to extract and process resources. The tough conditions in space, with harsh temperatures, radiation, and microgravity, add more complications. Moreover, whether such ventures will be economically feasible is still up in the air, given the high costs of space trips and the current lack of infrastructure to support big mining operations. Legal and ethical questions also present big issues. The international rules for space activities, especially the 1967 Outer Space Treaty, aren't clear about owning and using resources beyond Earth. This murkiness could lead to clashes over resource rights and environmental effects between countries and companies. Additionally, the possible environmental impacts of mining, like disturbing celestial bodies and creating space debris, present long-term risks to the space environment and future missions. While asteroid mining holds great promise for revolutionizing resource gathering and driving tech and economic growth, turning that promise into reality means tackling big technical, economic, legal, and ethical challenges. Finding a thoughtful middle ground will be key to enjoying the benefits of using space resources while ensuring the space environment remains intact for those who come after us. Collaborating across borders is essential for guiding the future of space exploration, encouraging teamwork, sharing resources, and spreading risk among different countries. Space missions are pricey and complicated, and no single nation, regardless of its tech skills or economic power, can handle it all alone. Through teamwork, countries can divvy up costs and tackle technical hurdles, turning ambitious projects into reality and speeding up scientific progress. Take the International Space Station, ISS, for example. It's a shining emblem of collaboration involving the US, Russia, Japan, Canada, and the European Space Agency, ESA. This lab in orbit shows how teamwork can drive research that benefits everyone on Earth. Beyond the ISS, projects like the James Webb Space Telescope, developed by NASA, ESA, and the Canadian Space Agency, demonstrate how joint efforts lead to big discoveries. These partnerships allow countries to swap knowledge, skills, and tech, boosting the global space community's capabilities. The spirit of collaboration also shines in planetary exploration, like with ExoMars, a mission by ESA and Roscosmos hunting for signs of life on Mars. This teamwork thrives on the different insights each country offers, leading to more solid planning and superior data analysis. Plus, working together on space missions strengthens political ties by fostering trust and offering a chance for diplomacy, reducing international tensions. This approach also reinforces the notion of space as a shared space, with achievements available to everyone. NASA's Artemis Accords are a testament to this, setting guidelines for cooperative lunar exploration with aims for peace, transparency, and sustainable moon resource use. Yet, challenges do exist. Different country priorities, rules, and policies can make negotiations and coordination tricky. Issues like intellectual property, data handling, and role sharing demand careful attention. But despite these challenges, the perks of working together in space exploration far outweigh the struggles. By teaming up, countries can achieve more than they would alone, unlocking new knowledge, uncovering new territories, and ensuring space exploration benefits all people. Watching meteor showers is a mesmerizing experience as these celestial events light up the sky with streaks of shooting stars, with some of the most breathtaking shows happening annually. The Perseids, which grace the skies each August, are among the most well-known and dependable meteor showers, famous for their brilliant, swift meteors, often displaying up to 60 meteors per hour at their peak. They originate from the remains left by Comet Swift-Tuttle and have been enchanting viewers for centuries, offering a spectacular night sky scene that often features fireballs, extra bright meteors that outshine many others. Another standout meteor shower, the Geminids, illuminates the December sky. Unlike many meteor showers derived from comets, the Geminids come from an asteroid named 3200 Phaethon. This shower is celebrated for its slow, colorful meteors, with colors like yellow, blue, and green. At its height, the Geminids can produce over 100 meteors per hour, making it one of the most abundant and reliable shows, a true reward for those who brave the cold to witness the spectacle. Meteor showers light up the sky when Earth travels through trails of space debris left by comets or asteroids. These tiny particles, usually no larger than sand grains, hit the Earth's atmosphere at incredible speeds, often as fast as tens of miles per second. This quick entry causes them to vaporize due to the friction with atmospheric gases, leaving behind bright streaks of light. Each meteor shower gets its name from the constellation it seems to radiate from, known as the radiant point. For instance, the Perseids appear to radiate from Perseus, while the Geminids come from Gemini. The reliable and timely occurrence of these events is thanks to Earth's yearly journey through these debris paths, maintained by the orbits of parent comets or asteroids around the Sun. This cosmic dance ensures that we get to enjoy these breathtaking meteor showers regularly, reminding us of the vast, ever-changing universe around us. Auroras, also known as the Northern and Southern Lights, are among the most captivating natural displays seen in the Earth's polar areas. These enchanting light shows happen when the Sun releases charged particles, mainly electrons and protons, and they interact with Earth's magnetic field and atmosphere. As the solar wind, a stream of charged particles from the Sun, reaches Earth, most are deflected by the magnetosphere, but some particles get funneled to the poles where magnetic field lines meet. The magical auroras appear when these charged particles collide with gases high in the Earth's atmosphere, especially in the thermosphere, ranging from 60 to 300 miles up. When they hit gases like oxygen and nitrogen, they get excited and emit light as they settle back down. The colors of auroras depend on the type of gas and its height. Oxygen creates green or red light, green at lower altitudes between 60 and 150 miles, and red above 150 miles. Nitrogen usually gives off blue or purplish-red light. Solar activity, such as solar flares and coronal mass ejections, CMEs, can amp up the solar wind, bringing more charged particles and making auroras more intense. During peak solar activity, auroras show up more often and can appear in places farther from the poles. These light displays can be stunningly unpredictable, shifting from gentle waves to bright bursts that change color and intensity in a flash. Auroras highlight the complex dance between the Sun and Earth, offering a glimpse into our solar system's connections. People in regions like Scandinavia, Canada, Alaska, and Antarctica often get to witness these natural wonders, sparking amazement and scientific curiosity. Cosmic phenomena like eclipses and transits provide some of the most breathtaking sights from Earth, enchanting both amateur sky watchers and professional astronomers. Solar eclipses stand out as particularly awe-inspiring events. They happen when the moon moves between Earth and the Sun, casting a shadow over part of our planet. Solar eclipses come in different types: total, partial, and annular. A total solar eclipse, where the moon completely covers the sun, is a rare spectacle that turns day into night and reveals the sun's delicate corona. These extraordinary events offer unique chances for scientific research, advancing our understanding of solar activity and atmospherics. Unlike solar eclipses, lunar eclipses are visible from anywhere on Earth's nighttime side and can last for a few hours. When you get to see a total lunar eclipse or a blood moon, it's pretty incredible. The moon turns a deep red because of sunlight scattering through Earth's atmosphere, which is a process called Rayleigh scattering. These events give astronomers a chance to study changes in the moon's environment and surface, while the rest of us get to marvel at a cosmic show that's captivated humanity for ages. Another cool celestial event is a planetary transit, where a planet moves right between Earth and the Sun. The most well-known transits are those of Mercury and Venus, where the planet looks like a tiny dark dot moving across the Sun. These are pretty rare. Mercury does it about 13 or 14 times a century, while Venus has a pair of transits more than a century apart. Transits are important to science because they refine our knowledge of planetary orbits and have been crucial for measuring astronomical distances. Conjunctions happen when two celestial objects appear super close in the sky, making for a stunning view that holds astrological significance in many cultures. One to watch out for is the Great Conjunction of Jupiter and Saturn, which happens around every 20 years. When it occurs, the planets are closely aligned in the sky, offering an impressive and meaningful show. These cosmic events not only awe us visually, but also provide valuable chances for scientific research. They help astronomers gather info on celestial movements and characteristics, bridging a connection between viewers and scientists and sparking our curiosity about space. Then there are events like gamma-ray bursts, GRBs, and other high-energy happenings that change our understanding of the universe. GRBs are intense gamma radiation flashes, the most energetic light form, lasting from mere milliseconds to a few minutes. They're split into two categories: short bursts under 2 seconds, likely from neutron stars merging, and long bursts linked to massive stars collapsing into black holes. Studying these bursts uncovered significant insights into star death and black hole creation, and they show how matter behaves in extreme settings. The amount of energy released in these bursts in just seconds surpasses what the sun emits over its entire 10 billion-year life. This energy gives us a unique way to study relativistic physics and how jets form and move, since this gamma radiation often comes from highly relativistic jets during such events. Observing GRB afterglows in various wavelengths, from X-rays to radio waves, lets astronomers explore the burst's environment, revealing details about the interstellar medium and even its host galaxy. Other high-energy phenomena like supernovae and active galactic nuclei, AGN, are crucial in shaping what we know about the cosmos. Supernovae, the explosive end to a massive star's life, do more than spread heavy elements across the universe. They also act as markers for cosmic distance. Type Ia supernovae have been key in measuring cosmic distances, leading to the groundbreaking realization that the universe's expansion is speeding up due to dark energy. This has reshaped modern cosmological models and added to the mystery around dark energy and the universe's ultimate fate. Active galactic nuclei, powered by supermassive black holes at galaxy centers, pump out high-energy radiation while gobbling up matter. Exploring AGNs helps us understand black hole growth, galaxy evolution, and the dance between central black holes and their galaxies. Observations spanning gamma rays to radio waves have shed light on processes like accretion disk dynamics, jet formation, and feedback mechanisms controlling star formation in galaxies. Diving into the world of gamma-ray bursts and high-energy cosmic happenings gives us a clearer picture of the universe's most intense events. This knowledge helps us understand how stars evolve, how black holes work, and how galaxies take shape. These ongoing investigations are constantly expanding what we know in astrophysics, revealing the core processes running the universe, and they set the direction for future studies, both through telescope lenses and in theoretical research.